slides. Okay, so good evening, everyone. Thank you for coming. So welcome back to Plan 252 Transportation Modeling. Okay. So, right, the agenda for today, we will discuss about IFN series. So, we will discuss about the ideal flow introduction. Okay. So I will start with random walk, and then we will play a little bit with the lab. Okay. And then we discuss about random cycle. Again, we have the lab. And then let's do manual computation of IFN. Okay, we do some practices. And then we can use IFN Excel add-ins. Yeah. From there, we can start to compute, okay, using Excel add-ins, also how to calculate IFN using based on Markov Chain. Okay. We have several labs available for you. If we have enough time, then we can continue with these topics, IFN equivalence, transport and calibration, IFN. Yeah. So, and next week, we will discuss about the policy generation based on IFN and how to analyze those policies in terms short term and long term. Okay. And then, of course, you will have, because next week is our last class, you will have your final project presentation. Okay. If you have enough time, you can continue with optional topics of network optimization, transshipment problems, logistic in terms of preference problems, and maximum flow. So this topic are optional. Okay? This is not for urban planning, but this is for mostly for logistic transportation. Max flow is for pipeline transportation. Okay, but this is also interesting because in this topic you will learn how to use genetic algorithm inside exam. Okay. So anyway, so the final exam will be on December 13th. Okay, open from morning until evening, and then I will give you the grading before the end of the year. Okay, so is that okay? Go to the model. You can go to model, okay, and see a lot of materials there for IFN. So our topic today is about ideal flow network. Okay. So these are the topics that we have done. So we start from here. Okay. There are several videos available in YouTube publicly. So this is the very introduction of IFN. Okay. So you can watch on your own. Okay. So how, yeah, it's just 5 minutes each. And this one also I make what is the meaning of random walk that we will practice today. Okay. And then this is very long public lecture about random walk and its ideal flow. You know, but this is like very comprehensive. So our first slide is this one, random walk. So you can download this. Today we'll discuss these 3 slides and these other labs. Okay. Okay then, random walk. Can you see my slide?
Yes.
Okay, good. So I will put you as almost. Okay. So let's start with a random walk. Okay. Our goal is similar to the classical traffic assignment, which you know from four-step model, which is trip generation, trip distribution, and then model split and traffic assignment. At the end of the all this classical model is to create a flow matrix. Okay. So the problem with classical paradigm is you need a lot of data, especially you need OD matrix, which is very expensive to gather. And traffic flow, you cannot count for all, so you only count for a few links. Okay. These are also data, which sometimes available, sometimes not. But the OD data is the main data in the classical paradigm that you need to do. Next, also the land use, which require you to project the land use in the future. Okay, and then you gather all this land use data for trip generation. Okay, so to overcome those problems, okay, so I created this simple technique of ideal flow network for transportation, okay, which we will discuss from today. Okay. So what is flow matrix? Yeah, flow matrix is just square matrix, which elements is the number of trajectories passed through the corresponding link. So when people come from their home to destination, okay, then they will produce trajectory. It is from home to the road and then to the next intersection and then next intersection until the end node, which is the destination. This all this sequence of nodes will create what is called trajectories. Okay, so you look at this notation. Okay, so these are the nodes V1, V2 until Vn. Okay, Vk, yeah, and then particularly each of this node, for example, I and J, yeah. So this must be next. Yeah? I and J must be the next one. Okay? So in that case, we will have flow is basically created by counting the trajectory on and its link. Okay? So we already practiced this last time. Okay? How to assign the trajectory into the network and then count the flow. Okay? And now from the flow matrix, you can also get the stochastic. Okay? So dividing each element of the flow by its the sum of the row, you will get what is called stochastic. So what is this stochastic matrix? Stochastic matrix represent outflow, yeah? Outflow probability distribution. Okay? So that means from one link, okay, once you reach the intersection, how many probability to turn left, right, or to go straight, or you turn. So these are the meaning of stochastic matrix. Yeah? Now, I will discuss the development, okay, how we discover random walk IFN itself. Yeah? It is based on random walk. Okay? So initially, back in 2014, okay, I have a research lab in Manila, and we discussed what will be the next project. And at that time, we said, how about we created random walk on network with this random walk has been used for stock market. So is it possible to use random walk for traffic and transportation? So this is what I did. Yeah. So I created random network. Okay. Of course, this is transportation network. So that means even a strongly connected network. Transportation network means from anywhere you can go to any other place and can go home, right? So that's exactly the definition of strongly connected network. Okay, and then in each node, say for example, for node 1, you select all the available links. So we assume constant probability distribution for each node. That probability distribution is up to you to decide. Okay, so at this point, I just put equal probability, and then every time the agent, the agent move, okay, so we record link flow, which is the sum of the trajectory. So this is a very simplified version where the edge length is just one, and then the agent speed is just one also. Yeah? So each agent jump from one node to another at one time step. Okay, and then the agent will keep moving until time is infinity. Okay? So for about 2 weeks, I just run all of this simple simulation and random network. Okay. This is just one of example of flow distribution. Okay. The flow will go up and up and up until infinity. So it's practically useless. Yeah. The flow itself is useless. So this is important. Okay. If you just do random walk and then get the flow itself is useless because the flow will always go up increasingly until by the number of agent and the time up to infinity. So it will become infinity, 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 infinity. And the zero is personally no links, right? The one that has link will have infinity. But look at these numbers. Can you see some pattern? Anyone can see the pattern here? Look at the numbers. If you can see the approximation, okay. For example, here, yeah, this is 8,000. This one is 17,000. So 8,000 times 2 is about 16,000, right? But this is 17,000. So roughly 2 times, isn't it? And then this is 17,000, this is 34,000. So about roughly 2 times. The same thing probably. This one is roughly 2 times. This is almost the same, okay? Right? So if you just see roughly, there are some pattern, but if you just look at the individual number, they are very different. Okay? And there is no pattern. Okay? The same thing, for example, here, I run 200 agents at 1,000 times steps, I will get this flow matrix. Yeah, this is the adjacency matrix. It is the network structure, right? And these are the network. And if you use the pattern, okay, eventually, interestingly, yeah, it will become integer numbers. Yeah? So this pattern, yeah, say for example, if I divide all of these numbers by the minimum, and then I run up to infinity, yes. Is random walk approaching cardinal network? Not necessarily. Cardinal network is a little bit different. Yeah, later we'll discuss if we discuss if we have time to discuss the integer IFN. Yeah. So cardinal network, yeah. So you already learned that. Yeah? So cardinal network is the minimum integer minimum integer of IFN. Okay, but random walk itself will not necessarily reach that numbers. Yeah? We can reach that number through random cycle, not random walk. Yeah. Anyway, so asymptotically, all this number, which is random, okay, will produce integer number if we define with certain statistic of the flow. Okay? What is statistic of the flow? Statistic of the flow can be total, can be maximum, can be minimum, can be the standard deviation, can be the average. Okay? These are the statistic of the flow. Of course, when we say statistic of the flow, not including the zeros, so only the positive. Okay, and not only they become integers. Okay, if you look at the sum on the right hand side and on the bottom here, yeah, the sum of inflow and the sum of outflow, it will exactly the same pattern. Okay, And that is actually the node vector of each node. Okay, so again, I have another, yes, I have, say, another random network. Okay, and what I did is running this into simulation. Yeah, so I will show you the simulation. Let me, here. This is purely in Excel. These are the stochastic matrix I set. Okay, and these are the flow. Okay, and then there's also relative flow. This is identified with the minimum of the flow. Okay, the network is on the right side, and you can see, okay, as we increase the time, okay, it approaching the relative flow, approaching integer. Okay, not exact integer yet. So this is just a few thousands. When the number increases so much, it will approach integer number. So this is interesting. So remember this, flow itself is practically useless, but it is the relative flow that is useful. Okay, relative flow, not the flow itself. So in here, I divide by the total flow. For example, you can start to see the pattern. Okay, and then if you are divide by the minimum and then run it for a long time, you will find the pattern with our integer IFN. Okay, so this is very interesting phenomenon. Okay, and you can try on your own. Okay, any strongly connected network, okay, you can draw on paper, and then you can run this random network. Okay, and it will always create integer with this pre-matching. Yeah, the sum of the sum of row is the same as exactly the same as the sum of columns. Okay, meaning the flow are preserved. Okay, so here are the relative flow distribution when we increase the numbers, and then when we divide, okay, with the minimum, we will get about these values. Okay, and then asymptotically they will reach integer numbers. Yeah? So again, yeah, this is asymptotic, not the actual value. If you use random walk, okay. So this is very interesting phenomena. Why? Because regardless the number of agents, regardless the simulation time, okay, when these two number of agents and time is very large, okay, the relative flow or the flow ratio, okay, will reach integer numbers. Okay, and so I said, wow, this is interesting. Why it is interesting? Yeah, because this represent link utilization. Imagine that before this, in the classical paradigm, what we need is data, isn't it? So you need to have the actual flow to be able to get the calibrate the flow inside the network. But now we don't need that. So we need only the network itself. Okay. So similar to the civil engineering drawings, so you have an architect, so you draw the buildings, okay, and then from there you know the load, and then you can calculate already the actual columns and slabs and beams, isn't it? So transportation has not been reached that level, so up to IFN. Okay, so here we have the network, then we can get the flow based on network itself. So link utilization based on network structure. This is the important part here. Okay, so based on network structure, you can get relative importance of that links. That means the flow represent inherent properties of the network structure itself. If we assume long time, yeah, Of course, day to day, dynamically can change a lot. But if we assume long time, okay, then this actually invariance. And the node are preserved the flow. Yeah, the total inflow is equal to the total outflow. So this preservation, yeah, of the flow, I call this pre-magic. Yeah? This is similar to magic matrix, but in magic matrix you will have all the numbers are the same. Okay? But this is not exactly the same. So we can have certain pattern here. Okay? But only the sum of flow is the same as the sum of in the columns and the rows. Yeah, they are the same. Okay, so if this is from and this is to, then this is the outflow, this is the inflow, right? That means the sum of inflow exactly the same as the total sum of outflow. Yeah, that's also represent the node value in the flow inside the nodes. Yeah? These are the meaning of the sum of nodes. Yeah? So let's practice. Okay, this random walk. So I created random walk like this. Okay, so you can practice on your own later. Okay, so I have say 6 trajectories. Okay, again these are random generated, so you can generate later in the lab. Yeah. So say I have this first trajectory is A, B, C, and then second is B, C, D, and so on. Yeah. So let's say I have the A, B, C. So that means now the trajectory we need to chop yeah into links, right? So A, B, and then B, C. Yeah. So these are the 2 things. So look at this. When we assign these 2 links, yeah, in the trajectory, so we will have A, B here adding, okay, and then B, C here adding here. Yeah. So there you will see this flow matrix I draw in this figure. Okay, and then you can sum. Okay, this one divided by that. So 1 divided by 1 is 1, right? 1 divided by 1, 1. The rest is still 0. Yeah. So next trajectory we have BCD. This is just example. Okay, so that then you again decompose this trajectory into links, right? So we have BC and CD. Okay, now again you add. Okay, assignment is not just assign, we need to assign and merge with the previous values. So previously we have the 1 and 1 here. So then we merge the new network with the new assignment. So in this case, 1 and here, 1 and 1 here. So BC and CD. Okay. Then the network updated. Okay. And similarly, the stochastic matrix also updated. You look at here, the network is not fully utilized yet. There are still 0, 0, 0, yeah, in the links. So then we assign the third trajectory here. Okay, so this trajectory consists of 4 nodes, so that means we have 3 links. Yeah, C, B, B, C, and C, A. Okay, then again we assign, we add to the existing flow matrix. Yeah. Now you can start to see the stochastic started to develop. Right? So because we have 1, 1, 1 here, so 1/3, 1/3, 1/3. So we have this 1. Okay. Not yet fully utilized because these are still 0. Next, we have the 4 trajectories. Okay. Again, we have how many? 1, 2, 3, 4, 5. 5 nodes. That means we have 4 links. Right? So again, we update. Okay. And now you can still start to see the stochastic matrix better develop, and then this is already fully utilized network. Okay. So all the links are positive flow. Okay. So up to here you can stop actually, but because this is random walk, okay. So we need to run until infinity supposedly. Yeah. But we have only 6 example, 6 trajectories as our examples. So let's continue. Okay, so these are the next trajectories that we have. And then again, we updated links. Just every time you have the, for example, TB, yeah. Okay, so look at the node TB. TB was 1, okay, and then now we add TB, so now become 2. Okay, so 2 divided by 2 is 1. Yeah? Same thing, all of this when you update, you will have the updated flow matrix and updated stochastic matrix. Okay? The last trajectory is this one, A, B, C, D. So we have 3 links. Again, we assign, and you will see the final result. It is quite interesting because now the probability to turn left and right and straight will be fully developed. Okay, so remember, ideal flow is asymptotic values. Okay, when you have many trajectory data and then assign the network with the manner described in this example, then you can get the flow matrix. Okay? And then when the flow matrix is getting larger in terms of the numbers, and then you divide with say statistic of the flow, which is the minimum, maximum, total flow, or average or standard deviation, you will get the flow. Okay, and the asymptotic values, this will become stable with this known as ideal flow. Okay, from there you can calculate the stochastics. Okay? And the stochastic matrix also stable. When it reaches certain when the data increase so much, it will become certain values. It is stable. Okay. So with that, let's go to the lab. So you go here, the random walk on network lab. Yeah, this is still under develop, so you can see the folder dev here, under develop, not yet fully developed yet. Okay, so in this lab, okay, you can play. Okay, so you can also create any network. Yeah? If you want, you can create any network, not necessarily ideal flow. Okay, so you can have general trees network. See, you can have a cyclic network. You can have binary tree. You can have weakly connected. You can also have flow network. Okay, let's try with ideal flow. Okay, and the number of nodes you can create. So say I created this random network. Okay, based on this network, yeah, I have five nodes here. Then you can generate a trajectory. So you can set how many nodes per trajectory. Okay, so I generated here. For example, I have A, B, C, D, E. Okay, I can generate again. Okay. Now, once you generate this, of course, when you want to generate, you can start with what node. Yeah, for you can say, I want to generate from node. Oops. Okay, let's generate again. Okay, I want to generate from node P. There, it will start from node P. So, yeah, and you can set only 3 nodes. Yeah, it will become only 3 nodes. Yeah, and then once you generate the random walk trajectory, what you will do, you apply. Yeah, so once you apply, you will see. Okay, so I have this 3 VE. Okay, so you can apply the random walk, and then you can repeat. Yeah? How many times you want to repeat? Yeah? So if you want to repeat 1 time, 2 times, and so on. Okay, so you can repeat, and eventually from here you can get also the statistics. Based on the statistics of the flow, you can get the relative flow. These are the relative flow, and say I repeat 1,000 times. Okay, so I get a very big number here. Oh, and now if you look at this, okay, when we run a lot, yeah, you can start to see the relative flow is getting closer, yeah, getting closer to each other, and so on. So these are the essence of random walk. So you can play on your own, okay, for this random walk, and then tell me if you have any feedback. Okay. Now, any feedback that you want to give or question or comments? So the next lab that you can play, yeah, is random cycle on network. So you can go to random cycle on network. Okay. And I already open that. So you will have similar to a while ago. Okay. So again, you can play different, you can generate different random network. Okay. So every time you can generate different random network. Yeah. So based on this random network, for example, I make it 4 nodes only. Okay. So based on this random network, now you can generate random cycle. Yeah, not random walk, but random cycle. These are very long cycle generated. Can you see? And what's the difference with random walk? In random cycle, okay, once you create a random cycle, and when you apply this random cycle to the network, okay, automatically it will become IFN. You see this? This is already IFN. Okay, even if one cycle alone, okay, it's automatically IFN. You see? Okay, so this one is 2. Okay. Oh, you'll have some problems. So you can generate another random walk and you apply again, and so on. Okay? So then you can apply a random cycle, and you're supposed to get the IFN, and relative flow is also supposed to be IFN. There is some things still wrong in the computation of this lab. Anyway, so this is still under develop. Okay? So you're supposed to get exact the same. This, I don't know why this is not the same. This is supposed to be 1. So, anyway, so the idea is if you add cycles, okay, in initially you have blank network and then you create the cycles, okay, then it will become IFN. Okay, so if you can use Python, there is also ideal flow network. Yeah, yeah. if you can use Python, you can also use this one. So these are the Python library for IFN. Okay. So all you need to do first is to install. Yeah. So this is to install. You pip install this one, copy, and then after that you can try this example. For example, yeah, this is how you add links, how do you assign trajectories, and so on. Yeah. So, and the documentation is quite massive, actually. You have two versions of documentation. It is from the read the docs. Okay. And if you go back to the GitHub, yeah, if you have any issue with this, this is open source. So if you have any issues, you can go and post it here. Yeah. So in this GitHub, if you go here and click the documentation, it will go to repository. Okay, and these are a lot of tutorials about how you will use IFN in Python if you want. Yeah. So the API is more than 400 API, yeah, 150 API. So this is quite massive, quite a lot to study on your own. Anyway, so let's come back to this one. Okay, so using random walk, you need to be asymptotic to get the IFN. Using random cycle, you're supposed to get exact IFN at once. So that's the point there. Again, is there any question, any feedback from you?
Sir, I have a quick question.
Mm-hmm.
By IFN, you mean that the matrix that would be generated should be pre-magic, right? Or that's different.
IFN mean pretty much
Ideal.
reducible.
Yes.
Yes.
Oh, okay.
Yes. Pretty much irreducible. Okay.
Copy,
So
sir. So, the network that's in Moodle at the moment has some issues. That's why
correct,
it's
correct, correct,
generating. Okay.
correct.
Copy, sir.
So
Thank you.
the one didn't develop because the folder is developed. Mean it's not yet really good yet. So I just presented for you, but the idea is supposed to get pretty much, but it's not pretty much here, right?
Yes, sir. Because I thought I was doing it wrong again.
No,
That's what.
no. It's the program that is still wrong because this is still under development. Yeah, but
Okay.
thank
Copy,
you
sir.
for this feedback.
Thank you.
Okay, let's do it manually. Okay, on scratch paper or in Notepad. Let's do that. Okay. Now let's do it in Notepad. Let's do this. Share. Okay, so I will do go to the Moodle, and here there is a manual computation IFN. Can you see? And this slide. Okay. So we will do a lot of practice, and each of you should have at least one practice. Yeah, I think I have a lot of practices here. Okay. So okay. So in this lesson, you will learn how to compute IFN manually using just paper, pen, and calculator. Okay. And you will also learn the characteristic of IFN. Yeah. So what is IFN? Steady state. Yeah, steady state means you run very long time. Okay, relative flow distribution. Okay, it's not the flow but relative flow in a strongly connected network. Yeah, strongly connected network is basically irreducible, where the flow are conserved. That means very much. Yeah, and this is based on Markov equilibrium. Okay, so IFN is network, so that means a digraph, yeah? Directed graph, or a matrix. And so you can represent it as network, as matrix, and adjacency list, and so on. Okay? So it's a special directed graph where the matrix is irreducible and premagic. Yeah? So what is irreducible? Strongly connected. Okay, so this represents network structure. Yeah? How about the flow? The flow in premagic. That means the total inflows is equal to the total outflows in each node. Okay, so the flow are preserved. As simple as that. Only that? Yes. Okay. So we have the Python code available. Okay. And you want to do transport also, this is in Python. Okay. I have an Excel add-ins is also available in Revolut 2, but you get this one, I think version 2, the one that I push publicly. The one that you have in Moodle is version 7, which is much more advanced than the one in public. Okay. So now also have a lot of tutorial on IFNs. I also develop in MATLAB, which is still experimental version. Okay, so question is, why are we going to use IFN? Yeah? So IFN was initially developed for transportation, yeah, traffic flow network. So, but eventually it goes to beyond transportation. Okay, it now being used for mostly AI, actually, for artificial intelligence, data science, data mining, and automation. Okay, so it can automate robot automation. Okay, and there are some people who apply IFN for medical, also for agriculture, yeah, for industrial engineering and so on. So these are now become modeling metaphor. Okay, so it's just naming convention which come from transportation. So we are the first. Okay, so that's why the jargon, okay, the terminology still follow transportation. Okay, we have flow, we have congestion, we have reducible, strongly connected, we have premagic. These are transportation jargon. Okay, so other field will follow us practically. Usually we follow other field. So now other field will start to follow us as a transportation. So as long as the problem at hand, okay, can be formulated as flow equilibrium in a strongly connected network, then you can use IFN as your modeling tools. Okay, what is the advantage? Of course, is directly you get a long-term solution with a stable equilibrium. Okay, actually the formulation is based on maximum entropy. Yeah, the flow are conserved, and you require only parsimony. Yeah? Parsimony means very minimum. Yeah, stingy. Parsimony, minimum data, and it's automatically adjust if you change the flow. Okay, and it's based on network structure. Yeah? So mathematically sound for network assignment, and you can also get other equilibriums. For example, the Nash equilibrium, selfish equilibrium, and Pareto optimality, we can also get that based on here. Yeah, we have our own premagic equilibrium, which actually the same as Nash equilibrium and Pareto optimality. Yeah, next week we will discuss about that when we do policy analysis. Yeah. So what's the limitation? So you cannot use IFN for modeling metaphor in your field if the problem is not in system equilibrium. Yeah? If you cannot present that problem into flow in network, or if the network are not connected, okay? Or any of these four assumptions are not satisfied. Yeah. So for example, they are not strongly connected, the flow are not balanced, okay, and they are not stochastic, and they are not long-term equilibrium. Then you cannot use IFN. Okay? So when these are satisfied, okay, then of course you can use IFN in any field, not just in transportation. So I hope this is encouraging enough. Okay, so what are the characteristics of IFN? Number one, of course, strongly connected. Okay, that means from any node can go to any other node and go home. So communication network, transportation network, of course, must be strongly connected. Okay, so that's the basic. Yeah. So the flow is preserved. So that means again, total inflow equal to total outflow. My jargon is called premagic. Sum of rows must be exactly the same as the sum of columns. Yeah. Okay. Now, because this is a relative flow, that means you can multiply it with any positive scaling to produce the equivalent IFN. Yeah, that preserve the stochastic probabilities. Yes. So, this is very good question. Can IFN be used as the deterministic traffic scenario or only stochastics? This is a very tricky question. So, IFN itself is based on stochastics. Okay, but the computation, because you set the stochastic matrix as constant, so the computation becomes deterministic. So that's my answer. Okay. So the basic is stochastics. But once you set the stochastic matrix as constant, then it becomes deterministic. Okay. But the basic still is stochastic. So that means this is a strength, not weakness. Eh? So that means if you really want to be stochastic rather than deterministic, you can change the stochastic matrix. Okay, but if you want to no, I don't want to do stochastic, I still do it deterministically, then preserve that stochastic matrix as a constant. Okay, so yes, the basic IFN is stochastics. Okay, but once you set the stochastic matrix as constant, then it becomes deterministic. Yeah. Okay, so you don't need random numbers. Okay, and as I showed a while ago in the random walk experiment, okay, so the network should be fully utilized. Yeah, so all links must be all link flow must be positive. Okay, so look at this example here. Here we have inflow is 5, it then become 4 and 1, right? So here I have 4, and then you have 2 and 2, right? Going in is 4, going out is 2 and 2. And then going in here is 2, and then from there is 1, then 1 plus 2 is 3. So this one exact, right? And then 3 going in here, and then 2 going in here, and going out is 5. So this is Riemann-Jigs. Okay, and these are also strongly connected, then this is okay. Okay, so and if you want to make it more general, then of course you can just put XYZ here. Right? So say you have set this one with X, this flow is X, and this flow is Z, and this flow is Y, for example. Then because this is going in is Y and Z, then out must be exactly, oh sorry, X and Y. Yeah? Then the out here also X and Y. And then there's a Z here coming down, then X plus Y plus C at the bottom. Yeah. And then from here, you distribute again, now become X because this is already X, then now become Y and Z. And then now check the last node here with this, again, you distribute as Y and Z. So that's how you check. Yeah? So each node you need to check whether they are the sum of flow in equal to the sum of flow out. Okay? So irreducible means only connected. Okay, so that means from any origin node, you can go to any other destination node and can go back. Okay, that means there is a path between each pair of node. Yeah, this is that. So, when you want to use this for other field, so what's the meaning of strongly connected or irreducible? That means integrity, yeah, unity, wholeness. That means a feedback loop or karma system. So basically, irreducible means long-term system thinking. Yeah. So there are many things that we can use as irreducible, transportation network and communication networks. Yeah. even in closure in group theory and any equivalent relation, they are also strongly connected. Okay? You can check, you can create your own examples if you want. And the next is premagics. Okay? So what's the meaning of premagic? Yeah, the sum of flow in is equal to the sum flow out. That means, okay, this is a system in the equilibrium with the steady state. Okay, so philosophically, that means if you want to model justice system, okay, fairness, equality, balance, equilibrium, so you must create premagic system. So when you have premagic irreducible, that means wholeness with this justice, yeah, or fairness system. So you can apply in any field in this case using IFN. Okay, so let's do manual computation. Okay, so how to do? Simple. Okay, you can set any node origin, okay, starting point, and then you can set any flow into it. Okay, and these are the guide. Okay, if it is a single link node, that means there is only one in link, one out link. Yeah? One in link, one out link. Then the flow continues. Yeah, no need to change, right? But if you have multiple in link, okay, then the sum of all incoming flow at that node, okay, and you sum to become the flow at that node. And then when you have multiple outlinks, then you distribute this inflow among the outlink based on certain probability that already given with this in the stochastic matrix. Okay, so I'll give you an example so that you can see. Okay, so say I have this network, so and then I assign any value, right? So I just put 100 here. Okay, in this example, I said 50-50, yeah, equal uniform distribution, so that easy to compute. Yeah? So here we have 50 and 50, right, in node 1. So now go to node 2. Going in is 50 because we have only 2 links. So now become 25, 25, right? From here, go to this node with this. Now in node 3, 25, okay. Again, you have 2 outlinks. So because a probability distribution is equal, so you just set 12.5, 12.5, isn't it? Okay. In node 4, what happened? This is only one outlink. So in that case, 12.5 continuous. Yeah. So this is already ideal flow network. Yeah. So this is already IFN. Okay. So this is already IFN. Okay. But not integer, right? Okay. So if you want to make it integer, what you will do? Simple, yeah. You divide by the minimum. Yeah. So you get the minimum here. I all divide by 12.5. So this is become integer and also. Yeah. Easy or not? So with that, you can create your own network. You can draw, okay, your own network, any number of nodes if you want, okay. So, and then you can start to compute the IFN on your own, okay. So I give you example again, one more, okay. What is the ideal flow here? Okay, because this is only one link in and one link out for all, then of course the result will be all one, right? This is one, this is one, this is one. Okay. So the IFN is very simple, just 1, 1, 1. Okay. So all one in all links. How about this one? What is the IFN of this network? Anyone? So you can set any number here. Say I set 1. right? So this is going in to C is 1, then how about this one? Of course, this is also 1, and this is also 1, isn't it? Yes, correct. All ones. Yeah. Okay, so this is easy. Okay. Okay, so all one. Yeah, so you can see this is pragmatic, right? Ah, okay. This is more interesting. Okay. Can anyone compute the IFN of this? Assume equal outflow manually. And then you share your screen, okay? Practice 2. I have 13 practice in this slide. Okay, I want you to do from practice. You have how many people? 9. Okay, so practice 13, practice 12, practice 11, practice 10, and so on. So you can choose each one of you must be able to do one practice. Is it possible? So you type for everyone here, okay, your number, your practice number in the chat. Can you? You put in the chat, okay, your choice of practice number. So you put to everybody so that when you put first, that is the your number. So you can select first in, first serve. You want me to assign for you, or you can write on your own? Everyone will get. But no, not you can choose first, not rather than random assignment. Is it possible? It doesn't no excuse. Whether you are transit or using mobile, you can do it. Okay. No, we start not from practice 1, we start from practice 13. So you can start from practice practice 4 until 13. You choose. You just type the number. Um, okay. You can use mobile. Okay, there is a online version of this that you can also do. Okay. Mhm. More. Out, I will assign you one by one. Slide 43. Wait. Slide 43 is number 10. Okay, so Vin will do number 10. Okay, here. Vin Sanchez will do practice 10. Yeah, practice 10. Okay, and then who else? Where can we find the number? Which in the manual computation, IFN manual computation, you can see on the top of the practice that are numbers, isn't it? Oh, there are no numbers. Oh, yeah. Okay, so I will update that. Fine, I can update. Okay, I will update. Okay, I will update this one. Wait. IFN manual computation. Can you refresh your browser and then come back to the IFN manual computation? Sorry, you need to re-download. Okay. There are 13 practices there. So you choose which practice from practice 4 up to 13. Okay. Okay, plan number 6. Further down. Who else? And then who will do practice 4? Do practice 4. June, can you do practice 4? And Mark, can you do practice 5? Okay, Glenn, practice 6. Joyce, can you do practice 7? Sure. Joven, you will do practice 8 and 9. Yes. Joven, practice 8 and 9. Okay, good. Practice 6 and 4, 5, 6, 7. 8, 9, 10. So who else did not get? Win is number 10. Cup, you practice 11, okay? Oh, practice 8. Oh, practice is already got by Chopin, so you need to choose practice 12. Serene, you need to do practice 12. Is that okay? Who else did not get the assignment? Oh, I think all. Okay. So I'll write down here for all the chart. There. Don't forget your to claim your recitation. Some of you did not recite at all, so I don't know why. Some of you have already almost 60. This will create very big imbalance in your grade later. So once you finish, you can present. Done. Your assigned number is in the chat, yeah?
Both of them.
Okay.
So in practice 8, it is not impossible to do the IFN, sir. It's weakly connected because point A is a source node and point C is a sink node, sir. So it's not strongly connected because I can't go to point A again, but to point C, but there's no way out of point C, sir. Although the sum of rows and columns are the same, but as we can see, the sum of column A is 0, sir. So there's no way I can return to point A. Well, the sum of the row for point C is also 0. There's no way I can go out of point C if I go to point C, sir. So there's no IFN, sir. Then from the practice 9, sir, there's a situation that we add imaginary or what they call the cloud node, point Z. So I just add another row and column for point C, point Z, which connects, this way we can already connect A and C. So it will be a loop. There will be a way that I can go to point A and I can get out of point C. So I took the sum. Here's the, I will just highlight, sir. Here's the original part of the original situation, sir. The impossible IFN, but due to the added node, it can be now strongly connected, and it just sum of rows and columns will be equal. So I think this is the IFN of the.
No, that is not the IFN. That is the stochastic matrix.
Stochastic matrix, sorry, sir. The stochastic matrix of if we add the node Z.
So can you calculate the IFN?
Sir?
Can you calculate the IFN of this?
Wait, sir. Then just use, can we, okay, sir. I'll do the computation first, sir.
Okay.
Thank you, sir.
Yeah. The IFN theorem tells that there is only one node in the whole system. Okay. And if your network is weakly connected, you can make it into strongly connected by creating a dummy links between the weakly connected network, which from the sink to the cloud node, and then from the cloud node back to the source node. Yeah. So spiritually or philosophically, that means the cloud represent the higher dimension. Okay? So you can tell that this is like God. Okay? And weakly connected means the entity or person. That means if you are weak, you can connect to God. Okay? Then you become strong. So if you want to use metaphor. Anyone want to share screen? Okay. On number 6, right?
Yes, sir. I don't know if I was doing it right, but given is the stochastic matrix is this one. And it was mentioned that the node from the node A is 300. So,
Okay.
yes. So given that, it means that the flow for DA is 300, which is this one. And then since this flow is 300, everything that's going out of A is half of it, since there are only two, and that's 150 each
Okay.
for B and C. Given also that 300, sorry, how do I say this? Uh, D to B
Mhm.
is 1/4. And this B to A is 3/4.
Mhm.
So that's 3:1.
Mhm.
So if this is 300, this is 100.
Correct.
And if A to B is 150 and D to B is 100, so that's 250.
Mm.
And the same goes with C to C to D, right? C to D, because this is 150 and this is 250,
Yes.
because the sum that's coming from B is the sum of AB and DB.
Correct.
I don't know if I was doing that right.
Correct.
And since when I saw this pattern, at first I thought the minimum value would be 100, but then there's 150 and 250 that's divisible by 50.
Mhm.
So I came up with this
Mm.
relative. Is that right, sir?
Excellent.
Thank you, sir.
Yes. Excellent. Okay. So that's how you do it. Okay. Okay. So once you finish, you can practice other practice also, so that you can also learn the others. Okay. Glenn is finished. Who else? Everyone must do your practice, okay? At least one of the 13 practice you should be able to do it. Okay. June. June is practice 4. Okay, so this one is A to C, what 2/3, and then A to B is 1/3. No, C to B. There is no C to B. C to B is 0.
C to B is,
Yes.
oh,
No,
so
C to B is 0.
I assume that the 2/3 would,
No, it's not.
so it's a 0.
Yes. So still have one more missing. B to A is 1. C to B. C to B is 1. Sorry, C to B is 1 here.
C to B is 1.
Right. Okay. This is the stochastic, right? So
Right, sir. Yeah.
so this one not needed. If this is stochastic, the sum of row is not, the sum of column is not needed. Yes. So only the sum of rows, that's correct. Okay, so this is already irreducible. So now you compute, this is the stochastic, so you can put here S, right? So now can you calculate the flow? This is the probability, okay? So that means from A go to B with probability 1/3. Okay. From A go
Yes,
to
sir.
B with probability 2/3, but what
Yes,
is
sir.
the flow?
I will compute the flow
Yeah.
first.
So you create similar F matrix. Okay. Yes. So Ben, that's right. You want to do the same thing or you want to do different numbers?
Hello, sir. So I will assign a new number, sir.
Oh, you can do that then also, or you can do practice
Other practice,
2,
sir.
yeah, 2 or 3.
Okay, sir. I will try, sir.
I think 2 and 3 is the same. Mm. Okay. Oh, good. Uh,
My prof, I can't share my
okay, I can share it for you. And then you explain.
screen because I'm only using mobile.
Yeah, I understand. Share screen. I share your screen.
So for practice 12, Prof, it is assumed that X is 50. Yes, sir.
Practice 12.
So I assume from point A to B, it's 50. For all links, it's all 50, but except for D to C, which is 1. So that's times 2 of X.
Mhm.
So for relatively flow, that's the only
So 50, that's not correct. Can you see? Can you see here? I will show you. I will throw here. If this is going there is 50, right? And then going there is 50, then going in must be 100, isn't it? Not 50.
for the A.
From C to A
Yes.
must be 100, correct? And
Okay.
if this is 50 in, 50 in also, so 100, this is 50, 50, this is check. Okay, this is not correct in A. How about D? D going in 50, going in, this is check. Okay, how about this one? This one going in 50, in
150,
150, going out is only what 50 and 50, not correct.
100.
Ah,
Okay, Prof.
okay, so you make again. You correct this, okay?
Okay. Okay po.
Okay. Yes, Bill. Go ahead, you can share.
Okay.
Now already co-host, so you can share. Yes.
Sir, is my PowerPoint sharing already?
Yes.
Okay. So in this one, sir, we'll use multipliers on the stochastic to set up the flows on each
You are
link. So we
number
have
10.
10, sir. So for example, the LCM of the divisors of all the fractions in the stochastic is 30. So we use that as a multiplier for uh, the stochastics at A to get the flow for A, B, and link AC. So 1/3 times this multiplier 30, you get 10 and 20. So we can assume that AB and AC is 10 and 20, and then set up another multiplier for flows going out of node B and C. So since the stochastic at B is 4, we set a multiplier of 4y
Mhm.
to cancel the divisor to make it whole number sort of. And then at C, you have a multiplier of 5 times x. So flows at BA and BC, you can represent now as y and 3y, and flows at C emanating from C, we can represent now as x and 4x. Now we do balancing at node A. On the example, it's balancing between pairs of nodes A and B.
Yeah.
So to give additional value, I do the balancing at node C instead. So node A and node C. So we can get outflow from A, inflow from A, that's links BA and CA, should be equal to the outflow, which is AB and AC. So that is based on our setup initially, that's x plus y equal to 30. Then doing the balancing at node C, you have AC and BC going out, and then CA and CB going in. So that's 20 plus 3y, and here, and this, and x plus 4x, surprisingly.
Right.
Then it would be 5x. 20 plus 3y is 5x. Then we do solving systems of equation.
Mhm.
This would be our equation 1. So we just multiply it by 3 to get 3x plus 3y to cancel 3y
Okay.
here
Okay, very
on,
good.
on the second. So you get 8x is 110. So it's just algebra.
Yeah.
So
it's
x is
a-
13.75 and y is 16.25. So
Right.
we get this flow, although this is not yet the cardinal network or the maximum
Yeah.
integer, minimum integer, on a factor of 0.25 and 0.75. So we can multiply by 4 to make them whole numbers. So
Okay.
the resulting flow matrix would be the bottom right.
Correct.
And then it's pre-magic. So this is already
So imagine only 3 by 3 nodes. Computation is
Yeah, that's why I didn't select the star. The I think it's tedious to do.
right.
That's the
That's why we need to the software to help, okay, to do it faster only.
Yes,
Doesn't
sir.
mean that we cannot do uh, manually. Okay, we can do manually, but at the same time, the software will help to make it faster only.
Yeah, and then we can really appreciate why the setup for IFN is a linear algebra or linear
Yes,
matrices, because this should be usually systems of different
equation.
equations on n unknowns. So yeah, linear equations in n unknowns, which is better to set up in compact form or matrix form.
Correct, in matrix. Okay,
Okay, sir.
so excellent. So, I think this is the most difficult part, okay, because the probability is not uniform. When the probability is uniform, this is all one, okay? So the same setup, the same network structure, when the probability is just half, 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 okay? So that flow will become all one, as simple. But once they make it not uniform, then a little bit more complicated. Okay, excellent. So you can practice others so that you can also other simpler. Okay, Chopin.
Sir, I tried practicing another with practice number 2.
Hmm.
I'll just share my screen.
Please share your screen.
Can you see?
There. This is
So in
3.
practice number 2.
2 or 3, yeah.
So my technique here, sir, is I will first look for the node with the highest entry or exit, something like that. So
Okay.
I see that it's point E. So my target is the outflow in E will be equal to its inflow,
Mhm.
like that, sir. So I start with E since it's the node with many connections.
Mhm.
I started with point E and assigned a random number, for example, 100, going to A. So here's EA, sir.
Okay.
Then, assuming equal probability, the next, from E to A, I will go to node A. There are two connections, AE and AB. So the 100 users will be divided, assuming equal probability, AE and AB. So AE will be 50 and AB will also be 50. So from the 100, it will be divided to 2 since 2 connections.
Mhm.
Then I will next move to point B since I already used point E. So I'll just neglect it for this time, this week, this only, sir. So I will go to point B.
Mhm.
I've seen that there are also two connections. So at point B, BC, and BE,
Mhm.
from the 50, it will be divided again into 2, so 25 and
Mm.
25. Then one connection will lead to point E, so I will neglect it again, sir. Then I will go to point C.
Mhm.
So in point C, there are also two connections.
Mhm.
So the 25 users from B will be divided.
1.5.
So 12.5 C, E, and C, D.
Mhm.
Then the last node that I did not use is point D.
Mhm.
So there is only one connection. It will only lead to E. So the remaining 12.5 will also be 12.5. So it will return to point E. Then since I started with 100 point E, I should also end with 100 at point
Right.
E.
So you need to
So
check.
the sum here is 100. So I think this is the
Yes.
the flow, sir.
That's correct. Okay. So this is the IFN already. So if you want to make it integer, what you will do?
Sir, sorry.
If you want to make it integer numbers,
Integer, sir. I'll get the
minimum.
LCM, sir.
Yeah, the LCM is, how much is the LCM here? 2?
LCM for...
The LCM is 2. Isn't it?
yes, sir. Yes, sir.
So you just multiply by 2, everything.
Yes, sir. So it will be... I'll just copy, sir.
Just copy and then multiply everything by 2. Above, multiply by 2. Yes, and then copy to all.
There, sir.
So you can integer IFN already.
Yes, sir. It will be changed to 200. The flow total. Yes, sir.
Okay, super.
Thank you, sir.
Excellent job, man. Yeah. Yes. So, who else? Glenn is done. And Joven is done. Vin is done. June, Mark, Joyce, Cap, and Glycerin. Come on. Yes, we can also divide by 12.5 to make it 1. Okay, but the minimum, this is also okay. Okay. So remember, IFN is scalable, okay, by positive scaling. So you can put it up, you can put it down. Yeah. Why? Why it is scalable? Because remember, by definition a while ago, when we do random walk, okay, flow is useless. Okay, relative flow is something. Okay, so it is relative flow, not flow. Okay, even though we call it flow, you remember this is actually relative flow. That means you can multiply, you can divide with one number, okay, for the whole network. Okay, so it's scalable. And we can utilize this scalability of IFN to calibrate. Okay, that means if you have a certain flow that you already collected in the actual field. Okay, for example, one road that you collected is 25 or say 2,500 vehicle per hour. Okay, then you can put back to that network. Then you can set the multiplier of that link only. Okay, then you can use it for the whole entire network. Isn't that easier? Okay. Imagine that you can know the whole network flow just okay infer from a few network link flow that you collected on the field rather than everything that you collect. You only get only a few, then you can infer the whole network. That is the essence of IFN. And because we are dealing with link relative flow. Okay. Come on, those who did not, you need to show your work. ครับ
Hi, sir. I'm doing a different exercise. Exercise 11 was done already, so I'm doing something else.
Okay. You want to share your screen? Joyce. Where is Joyce? Oh, she disappeared. June.
Sir, can I try practice 3?
You can
But I'm not
practice.
sure if
You
I
can
should.
try other practices, okay?
I'll try practice 3, sir. I'll share my
Practice.
screen. Practice
If
three,
you
sir.
want challenge that practice number 11 and 12 and 13.
Already.
11, 12,
I just want to
13.
confirm, sir, if it's my answer is correct.
Okay.
Here, sir. Can you see my screen?
This is practice 3. It's the same, isn't it? Practice 3.
But the rule is I will start with link AB.
Oh, okay. You just different way to compute, yeah?
But the answer is the same, sir.
The answer is the same, correct.
Yes,
So if you use now the meaning is if you choose different link at as assigning the first flow, you will probably get easier answer.
Yes, sir. This time, sir, if assigned link AB with 100, it
Yes.
will directly go to the integer form of the matrix.
Yes.
So that's a shortcut, I think.
Correct.
So
Okay.
no more multiplying of LCM like that.
Correct. So if you assign now depending on where you assign, usually what we assign is something that only have one out links.
Yes, sir.
That is the easiest.
Yes.
So the more you practice, okay, the more you are familiar. And I hope you can use this also for your research, not just for the projects, okay, but for your own research and for your work later. Also. Software is available. So I really would like to encourage you to use this. Yeah. Okay. It's not perfect, but at least we have something that will be useful. Maybe when you see the policy analysis next week, then you can start to see the benefit of IFN compared to the classical paradigm. Something in the classical paradigm, okay, of transport planning. So you plan, right? So you collect the data today and then you make a plan. Then you create what is that? Traffic impact assessment. Okay. So after you plan, whether your result is correct or not, nobody can check, isn't it? Say you do a project traffic impact assessment or transport planning. Yeah? So question is, after you create this assessment, okay, whether it is correct or not, nobody can assess your work. That is the classical way to do. Okay? But that is not science, that becomes faith. Because people will just put faith on you that your work should be correct. Okay? So I have tried to break this. Okay? There is no way to say that your work is correct unless we can check back in the field that your work is actually correct. Okay. Why in the classical paradigm you cannot check? Because they are using average. Okay. When you are telling, oh, the average travel time in the network is this number. Who can collect the data of the entire city travel time? That's impossible. That's why you cannot check. Okay. In IFN, we don't do that. In IFN, we use maximum congestion. Okay. And then from the maximum congestion, you can check one link flow. Okay. From there, you can collect the data. Then you can check whether your computation is correct or not. So we base it on real flow that is in the field rather than just assumption of the average of the entire network. So this is real science, guys. Okay, something that you need to validate. Planning is not just wizardry. Okay, just doing some plan and then nobody can check whether this is true or not. Should be checked at that year, at that point. We need to know whether your computation, your plan, your prediction is correct or not. So using IFN, we need to know where and when it will be predicted at what value. Okay, so at this point, learn about IFN first so that you can get the idea. Okay. Who did not present? Mark. Yeah.
Still trying to do it. Sorry.
Even if you have difficulty, even it's incorrect, no problem. You just show so that I can help you and discuss about it. No problem. Like last stream a while ago. So. Oh, okay, good. Let me download this. And I will put. Oh. Hmm. This is what the stream is showing. This is correct. Yes.
Yes, sir.
Okay. So let us see. 50. Okay. Okay, explain.
So
No,
the given
this is still
stochastic,
incorrect. This is still incorrect.
I don't get to say for the 100
Okay.
at the flow matrix.
Okay. Okay, let's do the work of this here. Okay, so say you have A to B half and then A to D you have, right? This stochastic is given. Okay.
Yes.
Okay, so let's do that. Okay, where you want to set your number? Any? Initially. Say I will put here 100. Is it okay?
What I did was 50, sir.
Huh?
50 for 1/2.
Yeah, so this is 50, right?
Yes.
And then this is 50, right?
Yes.
Okay. So you get A to D 50, correct? And then A to B 50. So then C to A, this one should be 100 because this is the one that you sent, right? This should be 100. Is that correct?
Okay.
And then this is should be 100. And this is, now let's say C to B. Where is C to B? This one, right? Okay, so you assign here 50. Why you assign 50? Cannot be 50. You know why? Because the probability from C to A is half, and then from C to B is also half, right? That means if you put this is 100, they must be the same, correct or not?
Yes.
Yeah, so this one must be 100, cannot be 50, right? Because they are the same probability. See? So in this case, C to B should be 100, right?
Okay.
Okay. Yeah. Okay. So this is going in 50, going in 100, so 150 already, and then going there we don't know. B to D we don't know, and then B to C we don't know. So then you can say this is X and this is Y. But we know that X plus Y, okay, is equal to 100 plus 50, isn't it?
Mhm.
That is 150. Yes. And then this one is X, this one is 50. That means this one should be X plus, this should be X plus 50. Is that correct? This one is X, and then this one is 50. So in D, this is the only one out, right? So this must be X plus 50. And then in C, so we will have X plus 50. Now in point C here, you have X plus 50. Okay. And then you add again with Y. Okay, going out is how much? This is 100 and going there to, so become equal to 200. So X plus Y is 150 plus 50 is 200. Okay. So so here is 200 in C. This one should be 200. Okay, so in here is supposed to be also 200. We know the sum. Okay, but we don't know B to D. B to D is X, right? Correct. And then B to C, this is Y. So here I don't know, so I put just X plus Y. This one also X plus Y, correct? B to A is 50, and then plus in point B, this is 100, so this is supposed to be 150. Is that correct? How about in point D? Where is D? D here is 100 plus 50, so this one must be 150. The same thing here, this is supposed to be 150. Because this is pre-magic, this is supposed to be the same. But, this is already 100, correct? And then this is 150, which is x plus y. This is 200 and 200, is correct? 150 and 150. So the only things that you don't know is x and y. Okay. But D to C, where is D to C? No, this is D to C is x plus 50. Why you set 100 here? We don't know. So this is supposed to be x plus 50, this one. Plus 50. Is that correct? X plus 50 equals
Yes,
150. So in that case, x is equal 100.
100.
Yeah. So x is equal 100, then y is equal to 50. Is that correct? So you can simplify after that. Yeah. So we get everything. So we have B to D. This is 50. 50, right? And then we have B to C, which is Y. Sorry, B to
50.
B to D is X, 50. And then B to C is, this is 100, is that correct? Okay, then the rest is the same. So here is X plus 50, X a while ago is, this is X, right? So this is 150. And then the rest is the same as this one. So this is 100. This is, how much is this a while ago? C to B. C to be 100. 100. A to B is 50. And then A to D is another 50. Check if this is correct. This is 100, this is 100, this is 150, this is also 150, this is 200, this is, oh no, this is still incorrect.
You can see.
This is
150 to 50.
wrong. This is supposed to be 200. Why this is 250? This is not correct yet. It is correct. B to C.
150.
This is incorrect. This one is X. Yeah. 100 is 1. X plus 50, right? X is 100 plus 50, 150. 150. What number are you?
So B to C is Y. That's why it's 50 only.
Which one?
At the relatively flow should be 50. B to C.
B to C. Yeah, this one must be 50. B to, oh, okay, this is incorrect. This is should be 50. So this is 200. This is correct.
Yes.
Yes. Okay, so this one 100. Oh, in that case, this is incorrect. The premagic properties must be, this one is exactly the same as this one.
Yes, sir.
Okay, so can you check? Some of this computation still incorrect. Your number is 12. Oh, okay, so 12. This is what I got in the slide. Number 12. You see? So initially I said CA 100, so then 50-50, the same as yours. Okay. And then now what we want is, this is 50, right? And then we need to divide by 2 here. Right? So that I can divide by 2, so I assume here is 2x. Okay. So in that case, I can put it as 25x, 25 plus x, 25 plus x. Right? So once you make it 25 plus x, so then you add here 50 plus 25, that is 75 plus x. Okay. And then in point C, okay, I will have exactly correct, right? 25 plus 75, that is 100, that is going out. And then we have 2x and then going out. Now, this is already ideal flow, but in x. Okay, so now you can set any x, okay, in order to make so that the flow, the probability will be exactly this one. Okay, so in that case, I can try, okay, and then we can use 50 so that the actual value will be, you can simplify into this value. I'm in presenter mode. Oh, wait. Let me see. Okay. Can you see it? So initially 100 set here, okay, and then this one become 50-50, right? And then because we want to divide into 2, so then we can set any value here. So I can put set 2x so that I can divide by 2. Then I will have 25 plus x, 25 plus x, right? And then we just add in D. So that 25 plus 50 now becomes 75. Okay. And at this point, we already have the ideal flow, but is in x. Okay. Now you need to set the x in order to make so that the stochastic matrix in C will be half-half. Okay. So in that case, going out is 100. So in that case, this must be 100 also. So in this case, x must be 50, isn't it? So once you get x is 50, then you can compute the whole things. So, yeah. Okay. Anyone else want to share?
Can I try, sir, practice 13?
Oh, practice 13. Yeah. Okay.
But I think the answer in the slide is a little bit wrong, sir.
Oh, really? Okay. Let
The
me.
letter C, sir, because 3 plus 5 is equal to 6 based on the slide.
Okay.
So
Maybe my answer is incorrect. Okay.
I'll just pick screenshot my answer, sir.
Yeah. Okay. So you can share your screen. um, you can share your screen. It's okay. Yeah. Did you share your screen? Oh, okay, share.
So I started with wait, sir. Started with point C, sir. So
Mhm.
C is equal to D plus T based on the
Okay.
link connection, sir.
So
Given that
D is equal
D is
to
equal to 7, I'll just use that as equation 1, sir. So C is equal to 7 plus 2 unknowns. Then I move to point D.
Mhm.
7 is equal to 7 S plus Y. So I can't yet get another unknown. There's
Mhm.
the two equations but already four unknowns. So I move to another point. So X plus A minus Y is equal to S plus T. I use the node um wait, sir. I'll just wait lang. I'll just get the illustrations. So these equations three, sir, I use point B,
Mhm.
since X plus A minus Y will be equal to B,
Mhm.
but B is also equal to S plus T, if I'm correct, sir.
C equal to
Point B, sir, is equal to S
B
plus
plus
T,
T.
and
That's okay.
it is also equal to X
And
plus
then
A minus Y. So that's my equation 3, sir. I just simplified. So 3 plus 5 minus Y is equal to S plus T. So 8 is equal to S plus T plus Y.
okay.
Then using equation 2, S plus Y is equal to 7. I put it here, sir. So 8 is equal to 7 plus T. I will get the first unknown T is equal to 1.
Okay.
So I then substitute it back to my equation 1. C is equal to 7 plus T. So 7 plus 1 is equal
Okay.
to C, which is 8. So that's the second unknown, sir.
Okay.
Then I move to another point, sir.
X plus A.
X plus A minus Y is equal to B. So 3 plus 5 minus Y is
Which
equal
node
to
is this?
4.
X plus A
This
minus
one, sir.
in node P, right?
Yes, sir. So I
Equal
know, so I
equal
got
to
Y is equal to 4. So
right?
8 minus 4. So it will be Y equal to 4. Then to get the last unknown, sir, this is not, this is wrong, sir. The last, wait, sir.
X is 3
That should be
and
S, sir.
A
This
is
S is equal to 3, sir, not Y. I just,
okay.
so using that last equation, sir, S plus Y.
S is equal to 3, that's correct.
Yes, sir. So it should be 8, 1, 4, and 3. But based on the slide sheet, it's written 6. So I thought I was wrong.
S is equal to B minus T, isn't it?
Sir, S plus Y is equal to 7.
S plus Y in T.
Using point D, sir,
That's
using
correct.
point
Okay.
D.
Okay. That's
So
equal to
yes.
7. That's correct.
So I got S is equal to 3. So my
S is
answers are C is equal to 8, T is equal to 1, then Y is equal to 4, then S is equal to 3.
Yes,
The-
that's correct. Okay. Good. Which one is the wrong thing in the slide?
C, sir, because 3 plus 5 is equal to 6. 6, it was written there, sir.
Okay.
Just a slight miscomputation, I think, sir.
Okay, I will correct it.
Thank you, sir.
Okay, thank you. So, interesting part of the last practice, last practice 13 is we want to make, okay, so that all the links will have a positive flow. Okay, so in that case, if, for example, B is equal to 3, then you will not be able to create a positive flow unless you change the network structure. Okay, so there are some limits. Okay, when you set that all the flow must be positive, then there is some limit that you can set the value. Okay. Okay. Good. Thank you, Jopen. Yeah. So, Glenn, you want to show something?
Yes, sir. I know that practice 5 was assigned to somebody else, but then I tried it also,
Okay,
so I'm gonna share my screen.
right.
And I also have a question, sir, because the answer that I got does not match the answer that was in the practice.
Okay, let me see.
So, this is the network that was shown. And then since there's only one link that goes to A, and there are two that goes to B and C. When you look at the fractions here, they're all divisible by 12. So I assume that A is 12. So that's B to A.
Just put 12 there, correct.
Yes. And this is the only link that goes to A. So this 1/4, if this 1/4 is 12, then um this 3/4 should be, that's 12 times 3. So that's 36. And if this is 2/3 and 1/3, this should be 4 and this should be 8. And
34 plus 4, 36 plus 4 become 40.
yes, sir. But then this is, if this is 36 and this is 8, that's 44.
Okay.
So I think that's what's wrong with
Yeah, I mean, that's like
this one,
wrong.
because the AC and AB were interchanged.
Yeah, okay. Okay, I got it.
And then for the RF, you just divide it by 4.
Okay.
Divisible, everything's divisible by 4.
Right, thank you. Thank you for the correction.
Thank you, sir. But I really had a hard time figuring it out at first because I was trying to write it on paper and
Right.
then I noticed the mistake. Thank you, sir.
Thank you. Super. Yeah. I'm glad to get this kind of correction. Okay. So not everything that I make is correct, but based on your feedback, yeah, we can start to improve. Yeah. Thank you very much. Okay. Okay, so Mark, do you still want to do it? Gab?
Hi, sir. I did 2 and 3. I'll just send it. I'm currently using my phone.
Okay. Go ahead. You can share your screen. Are you sharing your screen, Gab?
Sorry, sir. I sent it via direct message.
Direct messages. Oh, okay. Okay. So let me open that and share with others. And
Yes. So I did 2 and 3. So I'm still getting a hang of it.
and
So for practice 2, it started with 100 from E to A, and then
okay.
it started from A to B or B for practice 2.
So this is what Gap is making. Okay, so practice 2 and 3. Okay, good. So
Actually, sir, I'm just not sure what the value is for E to A and A to E. For P3, I think that's the only thing I was missing.
this is 50-50, right? Supposed to be.
Yes, 50-50.
Right.
And then I did the same thing for P3, but I'm not sure what the value is for AE. But I'm guessing it's also both 100 for AE and EA.
Um, the most important part here is when you see any node, okay, the sum of flow in is supposed to be equal to the sum of outflow, based on that probability that you set. Okay, so you have 100 here, then AE 50, AB 50, that's correct. So BC now become 25, and then PE is also 25, that's correct. So, and then now C to E, because this is already 25, now become 12.5 and 12.5, that's correct. And then, and of course, this is just continuation, so this is correct. So this is correct, all. Okay, and P3 is exactly the same as P2, okay, but the way,
But it starts from A to B.
yeah, the result should be exactly the same. Okay, so the only difference is you start from different links. Okay, so supposed to be easier. So you, instead of putting from EA, so you can start from AB. So if what happened if you put here is 100. Okay, then what will happen? So this is become 50 and this is become 50, correct? BE 50, that's correct. And BC 50. And then what you will do here, this is divided by 2, right? So 50 now become 25, 25, right? And then this is DE now still 25. Okay, so now in E, you gather already this is 25, right, in here. And then CE, how much is CE? CE is another 25, okay, 25 here.
Okay, so I add
B,
CE and
yes,
PE.
and then
Okay.
BE is 50. So then this is become, so total going in is 25 plus 25 plus BE, plus 50. So 100 total go in. Oh, but you still have EA, which we don't know. EA, we don't know. So let's call this X. Okay. And then you have EA. You also don't know. Is that correct? So,
Yeah, so EA is 100 because the inflow is 100.
oh yeah, correct. So this is already 100.
Yes. And then AE is 0
Or
because the flow in from A to B is 100. Right?
in that case, incorrect. Because you cannot make it 0.
Okay.
Okay, so in that case, you need to add a certain value. so that this will become
Okay.
positive. Okay, so you need to reduce. Is it correct? This is already 100. No, this is not 100 EA. EA is 100 plus X.
O plus X, okay.
Okay. EA is 100 plus X. And then this is X.
And then AE,
100. Yeah.
A2 is X.
A to E is X, correct. So
Okay.
then you need to assign X to any value, okay, which will make the probability correct. So you come back to the probability. So we need to put X the same as this one. So X must be 100 then. Isn't it? Because AB is 100 already, right? And then AB and AE is 50-50, right? Probability. So in that case, X must be 100. So that,
Okay. So the inflow from A to E is 100.
yeah.
So
this one becomes
E to A is
200.
200. Okay,
Correct.
got it.
This one
Okay, I got it.
Okay.
All right, clear.
Okay. So cannot be zero, okay? Okay, good. So good practice. So who else want to practice? Who did not share? Okay, so now let's do it in Excel. Okay, let's do it in Excel. And I remember, Mark, last time you give me the idea how to unblock, right? So you already have the IFN Excel add-ins, right? So let me share my Excel. Is this okay? So I'll put it here. So among all of this practice, which practice is the most difficult? And let's do that here. Come on, which one is the most difficult? Probably practice 11 is the most difficult, is it correct? Okay, so let's do practice 11 in Excel, okay? So I'll put S here. Can you see my Excel? A, B, C, A, B, C, right? And we have 0, 1/3, okay, 1/3, is that right? Here is 2/3. And then here we have 1/4 and 0 and 3/4. Here we have 1/5 and then 4/5 and then 0. So this is the stochastic matrix given. So I will call this S here. Is that okay? Underscore. Okay. So now I want to create a stochastic ideal flow. So again, IBC. C. Here A, B, and C. Okay. So if you use IFN Excel add-ins, all you need to do is equal, okay, n underscore, right? Okay, so you have stochastic matrix, you want to calculate the ideal flow. So you look for stochastics as, yeah, stochastic to ideal flow. Okay, double click. So I just make this. Okay. So you can set the kappa or you don't need to, it's up to you. And then you highlight everything like this. Okay. And then what you need to do is you click here. Okay. And then you press Shift Control Enter. Yeah. Shift and Control and Enter together. There. Okay. So alternatively, you can put kappa. Okay. So I put one here. Let us check, okay, whether it is true or not. Let us check. So I will put a sum. Oh, okay. Sum. Go up, right? And then this one is sum to the left. Oh, okay. So the sum kappa is 1. So let me get this color, okay, so that you can see. Okay, blue. Oh, let me get this blue or maybe this green now. Okay, so the sum is different color, so I will make it orange, and this is orange. Is this pre-magic? Oh yes, this is pre-magic. See, exactly the same. Oh, now I want to make it integer. How to make it integer? Okay, so here it is. Huh? So instead of this, okay, now I will name this kappa. Oh, sorry. I will name. Oh, I will name this kappa. Okay, so this is actually we input. So I put it yellow. Okay. Now here, I need to add kappa. There. Oh, did I name it? Yes, I named it. Okay, so here, I need to add to this kappa. No, then kappa. There. Okay. So I will copy this. Okay. And then I will highlight everything and copy and then Shift Control Enter. Still the same, yes, of course, still the same. The only difference is now I have kappa as parameter, so I can put this, for example, 17. Okay, it will, the total here, can you see, this becomes 17. If I put here 100, this will become 100. Okay, so practically kappa is the scaling, yeah, so that the total sum will be this one. Is this clear or not? Now, I want to make it integer. Okay, to make it integer, what you need to do is go here, okay, and then go to the number format. Okay, you go to fraction and then go to up to 3 digits. Oh, now you can see the denominator is 131. Okay, so what if I make this one become 131? Oh, if I make this into 131, so I get all integer. Good. Is this clear or not? Any question? Can you make it?
I'm encountering some errors.
Some errors. Okay, you can share your screen and I can help you. How to
So I tried it with the previous example that I did.
problem.
Sorry, but I can't seem to exit this one.
Wait. Oh,
To exit
oh,
from this
okay.
error.
Okay, let's do just but just click OK or just XXX. Yeah. Okay. So there must be certain error in the code. You just click X. This one.
Oh, okay. No.
Yeah. Okay. Or you could escape.
Yeah, I'm trying to click escape as well. I have to restart the slide, the Excel.
Really? Okay,
So I
so
have to exit from the Excel again.
okay, so because this a lot of computation, but there is some error. I don't know why. Okay, let's go out from here and then let's start.
Sure, I also encountered that, but I just click multiple enter until it just went.
Yeah, you click enter,
Okay.
it will stop anyway. So you don't need to go out.
There you go.
Okay, there.
That's very helpful.
Okay, so
But
can I see? Can you click here in this area?
okay. That's
Uh,
what I did with the manual computation a
uh,
while ago.
okay. Can we set this as numbers instead of
Okay.
no. Okay, so this is your number. Can you click here so that I can see?
Sorry. Oh, instead of formula, that
Yeah.
should be just 1/2.
No, that's okay. So this is
Okay.
already numbers, right? So
Yes. Yes.
okay. So now can you click here? Can I see? Okay, so let's put kappa here so that you can set, okay, and put number. And okay, so one is okay. And then let's come back here again.
Sorry.
Okay, stochastic diagonal flow, and then you edit here, comma. You put comma. Oh no, before the end of parenthesis, comma. Okay, and then put the kappa. Okay, and then close parenthesis. Okay, all the others you did it first. Only that cell first. Oh, no, don't do like that.
Okay. I have to do it one by one.
No,
Sorry.
no. You delete everything here and here. Just delete
Okay.
there.
Sorry.
Okay, good. So this is what can we come back here? Good. Now use your shift button, and then arrow button to the right and arrow button to down. While holding the shift button, don't drag. Just use shift.
Okay. Sorry. Okay. That's
Right, going
there.
down, going down. Okay, now use your mouse to click here. Okay, now press together, okay, shift and control and hold it.
Yeah.
Okay, and then you press enter. Shift control you hold and then press enter. There you are.
There you go. I will
Okay.
have to check it.
Yes, now you check the sum. Yeah, you can drag now. And then at the bottom, yeah, it's pretty much it.
Hmm.
It's the sum,
How, how,
yeah,
how
that,
do I
eh? You can put the sum first here.
Okay.
This should be 1, right? Okay, that's fine. Yeah.
There.
Okay, all right. So now you go to this one, you highlight, you select everything.
Okay.
Okay, and then go here, and then here, this one, number format, the last one. Okay, good. And then fraction, this is the third one. Okay,
That's
now you have
27.
27. Yes.
There you go. Thank you, sir. So
Then,
this is the same with this one.
is it the same?
No.
Yeah, okay.
Yes.
So
Thank you, sir.
the accident is the same.
Yes.
Great.
Thank you po.
Super, super.
Yes po. Yes.
Easy? Yeah. Anyone else want to? Yes. Jovin, go.
Sir, I have a suggestion so they won't encounter the error.
Yes, yes, please.
Since it's just like matrix operation and based from our stochastic matrix, sir, it's always a square matrix.
Uh-huh.
What if you highlight first if for example it's a 3 by 3, highlight a 3 by 3 cell before typing the n stochastic. So you won't encounter any error.
Okay. So you give name.
Ano, sir? Can I share screen, sir?
So, of course.
So here's what I did, sir. Since I know that this is the example you gave, sir, practice 11.
Okay.
Since I know it's the matrix of the flow matrix is also same with the stochastic matrix. I highlighted first the cell 3 by 3 also. Then I will type first
Okay.
equals in stochastic. So they won't encounter the error, sir.
I see. I don't know what caused the error.
Because a while ago, sir, I only click AA. So it's not the same size matrix, sir. So that's the
It
error.
was different size of matrix.
Yes, sir. Since that's only 1 by 1 and the matrix is 3 by 3, so you also need a matrix of 3 by 3.
I see.
Then highlight, sir, comma, kappa, close.
Okay.
Then that's the time we will control shift enter.
Hit control. Right.
So you won't anymore encounter the error. Just follow the size of the S
Yeah.
matrix, highlight a 3 by 3 also. Then before typing the n stochastic.
Good tips. Yeah.
Yes, sir.
Thank you, Jovin. Super. Right. Okay. I hope this is good practice. Okay. Last but not least, we can also try. Yes, June, you want to show something?
Want to ask for,
Yeah, you want to share screen?
yes, sir.
Okay, go.
I just
Okay, so
stop here.
this is S. Okay, and you can just add kappa in here, similar to what Joven did a while ago. So no, in here. Okay, so you can add comma. Oh, already did. Okay.
Yeah, sir, I did it already. So
Okay, so good. So if you already did it, okay, so 100, okay. Okay, so in that case, what you need to do is just put this into fraction. Okay, in the number form. Yeah, in the bottom here. No, not that fraction.
sorry,
Go to again here.
this one.
Yes, and then at the end, that one. And then go to the fraction here, 3 digit. Okay, good. There. Now you have you just need to multiply by 2 in this case. Now you got 200. You will get
200.
yes. Yeah, see, integer, right? So from there you what is this? This is something. Okay.
It's nothing, sir.
So you see, right? So once you get the fraction, you get the denominator of that. Okay, and then you multiply with the scaling. So you will get the actual kappa if you want to get integer.
Okay, sir.
Okay, super. So
Thank you.
very good. Okay, so last but not least, we can also do it in the online. If you don't have Excel, if you just have mobile phone, right? So you can do it online, yeah. So let me share with you the screen. So this is Excel. This is the one. So you can also do it online. Okay, so you go to the course. Again, you have a few, yeah. This is capacity to stochastic, stochastic to ideal flow. You can also have capacity to ideal flow. Okay, so let's do that. Yeah, capacity. Yeah, this one is capacity to stochastics. So in this case, you just create random value, or you can just type. Remember, the way you type is actually comma, okay, for the cells, and then don't forget to put a semicolon at the end of the row. Huh? So you can make it into a fraction also in here, so that you can get the stochastic matrix. Here, this is from stochastic matrix. Okay, when you randomize, this is the infraction stochastic matrix, and then you can calculate the flow matrix. Yeah? Okay. You can get the flow matrix, or directly, yeah, without stochastic matrix, you can also get directly. Okay, compute. Yeah, so I get this capacity matrix a while ago that you put in Excel. Okay, and then you can set the kappa. This is the total flow. Okay, and then you just get. Of course, if this is in fraction, then you get the fraction. So this fraction is so big. Okay, so try to do what you did in Excel in here, your capacity matrix. Okay, and then you can get the kappa and make it into integer. And then you click this blue button. Okay. And if this is correct, as per magic, you will see the pattern and the sum here. This is exactly the same here. So these are the pattern of pre-magic. Or you can ask here, is it ideal flow? Yes. Yeah. Is this pre-magic? Yes. Okay. So of course this is not. So the capacity matrix is not pre-magic. Yeah? Okay. Once you convert into flow matrix, you can get. So you can try this if you want. And these are the drawing immediately. And you can use press control. When you press control, you can move this. You can move the drawings dynamically. Okay. So I hope this is useful. Okay, so once you know how to compute the capacity matrix, means the number of lanes, right? So ideal flow is the flow. So how to get the congestion? Easy. Okay. The flow divided by the capacity. If this is the same unit, remember the keyword is same unit. Okay, then you get congestion. So the problem is your capacity is in lane, your flow is probably in vehicle per hour per lane. So it's not the same unit. So then you need to convert your capacity into flow. Okay. So for example, one lane is 1,500, right? So then you can multiply that so that you can get the capacity matrix with this already in. in the same unit as the flow. So once you have the same unit capacity and the flow, then you can divide, you will get the congestion. Try that. I think there is also no, there is no congestion. Okay. So there is IFN transport by matrix. I will put in the chat for everyone. This is the link. Okay. So when you use IFN transport by matrix, you will start to see how it actually works in the matrix way. Yeah. So exactly the same as your Excel. Okay. And you will see the multiplier also. Let me share. Okay. So say you are using this one, capacity is number of lane, right? So then one lane is say 1,500. Say now distance matrix is exactly the same 0 and 1. Okay. Now you can set this one, for example, 5, say 5 kilometer. This is probably 2.5 kilometer and so on. Okay. And these are the maximum speed in kilometer per hour. Okay. And then you can calculate. And you will get the capacity. This is the copy of this. Okay. The link distance, again, this is the copy. Okay. And then the speed matrix, just a copy from the input that you set. And then it will calculate the stochastic matrix and calculate this is the node value, and will calculate the ideal flow matrix and the congestion. Yeah. Because you said the congestion should be 0.9, then it will calculate, okay, so that the set congestion maximum is 0.9. Okay. With that, it will also calculate the travel time, okay, minimum travel time, and then the travel time, speed, and delay, and the other performance. Yeah. So that's now if you change this, for example, become PCU per hour, of course, this will become 1, yeah, multiplying. So if you use road width per meter, so I suggest say between 500 to 800 vehicle per hour per meter, right? So the rest is just based on your data. Okay. Why we are using 0.9? Oh no, we are not using 0.9 as anything. So you can just set anything. You have total flow as your basis, or maximum flow, or maximum congestion. Okay. And you can also use PPR or clean sheet here. Okay. So if you know the total flow, the kappa a while ago, you can set. If you don't know, my suggestion is use this one. Yeah. Initially, okay, so next week we will discuss more detail. Initially, you set the maximum congestion at any value, for example, 1 or 0.9 or 0.8. That's your initial value. Okay. From there, you will get the total flow. Okay. So based on the congestion that you set, okay, you will get the total flow. Total ideal flow network, yeah, the kappa. And then for the alternative scenario, you will use that kappa as your parameter. Okay, so once you have, for the second scenario, which is the alternative scenario, you will use total flow as your parameter, not the ideal flow. Then you will set, okay, oh, if the kappa is, for example, yeah, 1400 like this, what will happen? Okay, to the congestion. Yeah. Oh, apparently the congestion now from 0.9 now become 1.2. Yeah, for example. So in that case, your alternative scenario does not help. Your proposal failed. Okay. So of course, you need to create the alternative scenario that is actually better in terms of maximum congestion. Initially, you said, for example, 0.9, okay? When you propose a new scenario, should be less than 0.9, right? Logically, right? If the same congestion or above, that means your alternative scenario make the system worse. Notice, okay, when you change the structure of the network, suddenly, okay, this is actually you can see that the change in your network in one link, it will affect the flow in other links also. Okay, not just in that link. So redistribution of congestion is very important in this case. Okay. Any question? So you know how to compute the flow. Okay. Wait. What getting is ideal flow matrix? No, ideal flow matrix does not represent optimal. Yeah, it's just equilibrium. Okay, stochastic is based on like this. Why we use stochastics? Okay, because the travel behavior of people, okay, we assume does not change. For example, when you come from your home to your office, okay, you usually use the same path anyway, right? So in that case, in every intersection, the number of probability to turn left or turn right does not change. Okay, so what is the assumption of IFN transport? The assumption of IFN transport is the stochastic you assume proportional to the capacity. Okay, this is very big assumption. I understand that. Okay, but if you don't like this, so you get the actual data, and then you, for example, in certain intersection, you actually set up the camera, then you will know how many turn left and right and go straight, right? So in that case, in that intersection, you change the stochastic probability in that intersection. So if you have the data, use the data because that data represents the reality. Now, imagine you have one small town. How many intersections that you have? In Metro Manila, you have probably around 1 million intersection. Is it possible to install cameras so in all intersection? Probably not. Yeah, especially the small intersection, you will not install cameras. In that case, how I get the stochastic probability if they have no data that is available and it's too expensive to get the data, then you need to make assumption. So the easiest assumption that we can use is actually the proportional to the capacity, isn't it? So when the capacity is proportion, then you will get stochastic matrix. So probability is a simplified technique, yeah, to get the actual things. So it doesn't represent efficiency or inefficiency. So intervention, what you need depends on your proposal. So there are a few possible proposals that you can make. Okay, what you can do. Number one is you can add some more link. Add more links means, for example, you have a tollway. Okay, you have a new road basically. Or second, you can remove the link. Okay, For example, certain links, you make it into market, you make it into garden, I don't know, okay, or pedestrian only, so that the vehicle cannot move from that. So you remove the link. Third, you change the direction. So you make it one way, you make it two ways, okay? Or you reverse the direction. Fourth, what you will do is to increase the road widening. So you increase the road. This can be done not just adding the road, you can also remove the parking to widen the road, isn't it? Okay. And the fifth scenario is you actually reduce the road width. You may not believe, okay, that reduction of the road width can actually improve the situation. Not depends on where you will improve. Okay, it's not depends on adding link does not always improve. Road widening does not always improve also. Okay, it will just make the road congested in other place. Okay, so depending on where you will put. In this case, IFN become a very valuable tool to check where you will put your policy alternative. Okay. I hope with this you can try. You have the tools, you can try. Okay. Try to do it simple network first so that you can understand this, and then try with a bigger network as your project. Okay. Any other question, comment? Okay, so if not, so we end our class today. So it's right? So, and then next week, we'll continue with the policy analysis and alternative scenario. So please read the slides. Okay, and you can also practice so that we can have more discussion. And don't forget, you will present the last final project. Yeah. Okay. No problem. So see you next week, our last class. Thank you very much for today.
Sir,
you, sir.
can I stay for a bit? I have something
sure.
to get your head on.
Yeah.
Okay. I just put it. Also, sir, I noticed you've graded all the submissions we had.
Yes.
You haven't graded the network utilization.
Okay. I probably start. I will do it. Okay. And
Wait, sir. It's still loading.
okay.
Okay. This time, in which flyover A, for example, is very much deteriorated, so you want it to be replaced. But since the next flyover is just less than a kilometer away, so you want to replace the two flyovers as a single viaduct
Okay.
or a bridge. So what we did, let me open first the KML file I did for the network model.
Okay.
This one is in Pampanga. Is it showing now, sir?
Yes, I can see.
Okay. So here, sir, you have the first flyover. This one is the deteriorated. You have
Okay.
one that is westbound. Yeah, this one
Okay.
is west. This one is eastbound. So separated two existing flyovers.
Okay.
Now on the few meters away, you also have another flyover here.
Okay.
So first one, sir, you have two flyovers, both two lanes, unidirection. This one is two lane flyover, dual direction.
Hmm.
So no separation of the westbound and eastbound.
Hmm.
And then the road suddenly constricts here
Okay.
because uh, before the first flyover, this one is multi-lane. As we can see, sir, it was 6 lanes both sides,
Okay.
6 to 8 lanes in each direction.
Okay.
So more like the Commonwealth Avenue. But going here, this is now a narrow section. The section between those flyovers. Only 6 lanes
Okay.
or 4 to 6 lanes. Then you have a narrow flyover again, the one here,
Okay.
which is 2 lanes.
Okay.
Okay, sir. The this is the base scenario. The proposed scenario is that you combine these two flyover into a single 4 lane flyover, replacing it, effectively replacing both.
Okay.
So,
So,
sir, if I'm gonna model it,
mhm.
actually I did use the IFN transport.
So if you want to model it, okay, so its link should have the same, say in your actual road network, there are link that actually, say for example, 2 lanes suddenly become 4 lanes, or 4 lane become 3 lanes, and so on, right? So in
Yes.
that case,
Yes.
one lane should be exactly that lane, so that you can also see the bottlenecks.
In modeling, I should do lane per lane
Correct.
because here I did only the
The whole network. No, you should
yeah,
put lane per lane.
lane per
No, not
lane,
lane per
especially
lane.
on the
Link
intersection.
per link, but the one link supposed to be the same lane. One link supposed to be the same number of lane. For example, from 4 lane to become 2 lane. That means
Yes.
2 lanes.
Okay. So I break the link
Oh,
on the sudden change in the
correct.
trains or
That,
capacity.
in fact, that sudden change is the actual problem.
Here, this one. So I need to break here.
Oh. So
But actually, sir, on
Hmm.
this traffic flow, on this area, you can't do a right turn.
Okay, so you
So
can
no one is going here.
add, okay, left right turn, okay, which is not in the map, but you can add. Okay, if you go to IFN Transport, can you go to IFN Transport? They're online. Okay, so then
Yes, sir.
go to the
Yeah.
network.
Actually, I'm doing the OSM first. Before I set up that one, the network I'm showing.
Uh,
So I exported data
okay.
here as you've shown in class before.
Your scaling is 10. That is very big. Okay.
Yes, sir.
14 is very big.
So
Okay, 15 is fine.
so I use a manually select area and then highlighted the section
Yes.
I wanted to focus on.
Okay.
And then
And then get these numbers
yeah, I copied this
and then put it in IFN Transport.
here, the bounding box.
Correct. Correct. Yes.
And then, for example, you just download the OSM data set, right?
Yes.
And then it will
Oh,
show in
very
the
small. Because this is only until third year, and then you clean.
Yeah. Basically, I clip the manual selection.
Yes.
And the
That's okay.
IFN
So
transport,
you save this one so that you can save and then load back if you want, because you don't like to copy and paste that, right?
Yeah.
Again and again. So and then you just uncheck, so you just save. And then you can
download again.
yeah, you can check here first if you want.
Okay.
Okay. And download again. Oh, now better, right?
Yeah. So I can simulate even the residential in
Yes.
between.
But this is not strongly connected, so you probably need to add cloud node or oh yeah, you can see now the residential area. Change the scale so that you can see better. So change to 10,000, 100,000 or 75 probably. Yeah, 75,000 probably.
Too many nodes.
Yeah. So I think if you use 7,000 nodes,
IFN is
you
loaded.
cannot use
Oh, yeah.
it
Yeah.
online. So you need to
25,000.
use the Python one. See? Okay, you can.
It's better to use the Python
Yeah,
more
a
than
little bit different format, but it's the same program. In Python now depends on your hardware. Okay, here you use depends on your browser. So browser does not allow us to get very big memory because this is using your browser, right?
Yes, yes.
So,
Yeah, it's
so look at the
web-based
example so that I can
after all.
show you. Go to the network. Go to the IFN transport.
I'll have to load it.
Yeah, yeah. You already saved.
Actually, this
Robert.
problem is
You already saved, so you just upload it here. You don't need to.
okay, upload. But I saved the clean version,
You can open that.
not the.
When you save it, can you open that? That is only a text file. You check. Yeah, that one open. Can you see? Yeah. When you open that, yeah, I cannot see your. So that is exactly these numbers and these numbers, right? So you can edit there and then load it back.
Then you
Yeah.
done.
Yes.
Okay. So that's how you save it. The JSON file is just the coordinates.
Yes. Okay. Yeah, this one is because up to here, right?
Yes. Now it's showing the eastbound and westbound traffic, and then the error here would be it's just one direction. It didn't get the link.
Probably this is matter. This one.
To include.
Yes, probably you need to include certain road that because OSM is publicly edited. Okay, you can also edit, you know.
Okay.
Okay, so
but it's based on GIS, the OSM.
OSM is yes based on GIS, but at the same time, it's like Wikipedia. Everyone can edit.
Okay, sir. Suppose I have a data on daily traffic, for example. Let me, how can I share the screen?
You can.
Actually, I'm using it to develop an economic model for that project, sir, for
Okay.
project evaluation.
So I have an infographics here. I will find the
Yes, sir.
infographics.
So for example, sir, I have this data
Mm-hmm.
on those road sections. How should I use it to the IFN? Or should I use it to calibrate the model,
Okay, so this is the data that you have. Where is this in the link?
sir?
Where
Ah,
is
yeah.
you
For
can-
example, this one, MNR,
Okay,
on the link, sir,
this is the piece.
this would be this road.
Oh, I don't know which road.
This one, sir.
Ah,
Here. Hi, it's not showing.
not showing, not showing. I see your table, but I did not see your.
Yeah. Maybe I need to share the entire screen.
Yes.
Here, sir. Checking, you have the first flyover and then the
Okay.
second flyover here. So
Okay.
that road should be here. Yeah, this one.
Okay, good. So you identify the link number or the two node numbers. Yeah,
This one.
Yeah, for example, that one. So for example, 3727, is that correct? Or 3737.
7337.
Okay, so then go to the data there.
Okay.
Model. Okay, and then this one. So you have the node number, and then these are supposed to be the actual flow there. You can set. This is in PCU.
But should the actual flow should be in PCU, or I can use vehicle per day?
As long as you are using the same unit.
Okay. So be consistent about it.
Yes. Okay. So if
So
possible,
can load this
PCU because these are exactly different. If you use vehicles, that means large vehicle and small vehicle, you use equal value, right? So, but if you use PCU, that's probably better because large vehicle and passenger car will have different value.
Actually, I did that one to
Oh,
convert it to PCU.
yes. So PCU per hour or PCU per day, that's fine. Okay.
Okay.
So you need to identify which link and then you can input.
For example, this one, input 30,003.
So that 30,000 should be daily, right?
Yes.
So
Copy
this one, you need to know the node number, and then you copy.
How can I copy this?
There and the data. Actually, all of this you can put it into Excel,
Yeah. Actually, on the network also.
Right.
Maybe.
Right.
The
So,
link.
yes. So you
I
can
search
fix this.
737.
Yes. I understand in the box like this is complicated, but you can save it in Excel, CSV file, right? This one. So this one is the save and load. This is also save and load.
Here.
Yeah, there.
So this is
There.
the node 1 and node 2.
Yes.
Mod.
You remove everything and then that one.
So I just need to load one, not
Yeah.
not all of those daily traffic I had.
Only one or two is okay. And then what is, for example, 30,000, right? Well,
3031.
yeah, just copy. 30,316. 316. Okay, that's it. So you paste it on real world, and then that's it. You
So should I
15. You want to put that 15?
yeah, as
Yeah.
discussed in class?
Yes. Right. So
Okay. And then I go to result.
yeah. Oh, wait. One more in a model available.
Okay, model.
Your capacity is in what?
Vehicle per day.
Vehicle per day. Okay, so assuming this is vehicle per hour, right? No, capacity you set in the data a while ago. Is it in
Yes, sir.
vehicle, in number of lane or road width or PCU per hour?
Wait, let's go back to the network, sir. Base here should capacity.
Oh, 6,000. Okay, so this is already PCU per
So
hour.
this is PCU per
PCU
hour.
per hour.
So I need to convert to PCU per hour.
Yes, so 30,000 should be also in PCU per hour, so probably around 3,000 this one. About usual, yeah. This is in per day, right? So it's not the
Yes.
same unit, so you need to make it the same unit.
Okay. Yeah, per day. Then per hour.
Oh,
Should
per
I just
hour is
divide
about
by
10. If this is peak hour, so peak hour is about 10% of daily traffic, no? So I just divide by 10. No, divide by.
I think that's 0.8.
That's very big.
Sorry, you multiply, not divide.
Oh, okay, so you put it, okay, so that is about correct.
Should I
Yeah.
round up?
Actually, 2,500 is just two lane. Is it two lane?
Yes, sir. 2 lane for that direction. That's 4 lanes already.
4 lane, 2,500 is very low.
Really? For a 4 lane traffic.
Oh, for 4 lane traffic, 2,500 is very low. So say the 1.5 only. So one capacity usually 1.5 to 2,000, right? So
Yes.
the congestion is very low.
Okay. So now I can go to the results now.
Right. So result and then just calculate. Okay. Wait a minute. Before that, you need to check where your network is strongly connected or not.
Sir.
You calculate and you get. There are certain.
Actually, sir, we can check first. Yeah, it's strongly connected.
Okay. So
sir, playing with this web-based tool that you've shared. Actually, when we clip through the OSM, the network actually closes itself.
because
when
you
clipping,
clean
sir.
this one, because you clean
Yes,
it.
sir. So for example, on here, because it definitely won't close here, right? Because you
Right.
clip.
Correct. So it
The-
cooks itself because you clean it.
Yes, sir. The clean one introduces this cloud mode, going there, then going back.
Yes.
So essentially,
So if you don't like that, you can just add cloud nodes. Here you have
Cloud
two
node.
possible. Wait,
if I want to close from
This
here
one.
to this one,
can you see this?
sir.
In here, you will clean the same as before. In here, you will add. Try in the small network so that so that you will see the effect you try in the small network. Okay. If very big, you cannot see.
Clean to max, strongly connected
Correct.
component.
And then that one, the other one is just add a cloud. And
Add cloud.
yes, and dummy links.
Okay.
Okay. And when you get the result, it get warning. So it means yes, there are many links that actually larger than 100%. So is your network is very congested at certain links.
So I just have to check which link is
Yes, you can just download this. At the bottom, you can save as Excel.
here, export.
Yes.
Then I'll get this all tables. Actually, we did this in our group project also.
Hmm.
We use this web-based tool.
Yes. But
But
the web-based tool is
network-
only for limited number of link and nodes, no?
How many?
I think it's
servers?
about 2,000.
Okay. The network I am modeling is actually, or actually, sir, from the OSM, based on the clip data, I simplified those number of nodes into
Oh, that's
just 50.
yeah. If you use GIS to simplify, that's even better.
Yeah.
Yes.
But I find it very tedious to do because you
Yes.
do node per node.
It is. It is.
And then I get from your advice to do with that when the inventory shifted, especially on the number of lanes or capacity, you introduce another link.
Right. So when the capacity of the number of lane change, so you better use another link.
Yes, sir.
Okay. So with that, you can start to see, oh, the buildup of congestion is actually because of bottleneck, not because of these other things.
Yes, sir. And then I've run it actually using the model showing here on this idealization, sir.
Okay.
The one I did in Google Earth.
Okay.
So I put it in the IFN.
Okay.
So here. So I did one base scenario and another for the alternative scenario in which you have the viaduct. So I get link results for both.
My question. So comparing your base scenario and your alternative scenario, just
Okay, sir.
check the maximum congestion. So in the base scenario, you get total flow, right?
Yes, sir. Okay, base scenario.
Okay. Okay.
Total flow is this.
Where is the total? Okay, that is the total. This total flow you copy. Okay. You should assume that the total flow does not change for the alternative scenario, right?
So the total flow on the base scenario should be the total flow on the alternative.
Correct, because the demand does not change, correct or not?
Yes,
Total
it's the
demand.
supply it's the network structure that we're changing.
Correct. So the demand does not change, okay? You change the structure, okay? Whether now you compare the congestion,
Right.
the maximum congestion, just one link, that one. Okay, the maximum congestion can be in the same place, can be different place.
Yeah.
Okay, so whether the maximum congestion is actually improved or not. Given the same demand, change the network structure, will the maximum congestion change or not?
Sir, this is the left side is the base scenario, the right side is the alternative.
Okay, let me see the maximum congestion.
How can I go there, sir? On the link results.
No, here. In the network, go to the network tab.
Network tab. Okay.
See, the maximum congestion
maximum
is
166.
166. This is base?
Yes, sir.
And then in this scenario, improve.
So it improved.
Yeah, but still bad. Wait,
Uh, the
the
network is very much
kappa
good.
is the same or not? The kappa must be the same. The total flow. The total flow between
Yes, sir. Yes, sir. I'll show it again. The base and the alternative. Okay.
where is the total flow?
The summary. I go to the
Yeah.
summary.
Okay, 162, and then
Yes, sir.
it's the
Yeah.
same. Okay,
They're
good.
the
So in
same.
that, yeah, both still bad. Okay, but improve a little bit.
It's a less worse. Less worse.
Yeah, less worse, but still very bad.
Oh, from the very bad
166.
to 150. It's minimal. Actually, that's why NEDA is saying it's a minimal. If I'm gonna use it for benefit quantification, it might be minimal.
But if you look at the delay, the average delay is actually worse.
Sir,
Can you compare?
if average
From 3.5 now become 4 point something.
4. Okay, so
So that project does not actually improve.
mhm.
Yes, the maximum congestion improve a little bit. Okay.
Mm.
But if I see here, this value compared to this value, right?
Yeah.
Yeah. So here, yes, improve. Yeah. This one is the one that we see.
Yeah, in terms of congestion.
Yes. And network speed also improve.
Yes, because I introduced the 60 band and the 40.
Okay. So
This one
the
is
speed
based
improve.
on
The speed improved significantly.
but the
delay
delay
is
did not.
getting worse. I don't know why it's getting worse. So you need to investigate.
So basically, sir, if I expand the analysis to the outer road, would it affect
Probably
the
will get
analysis?
different result. Yes.
Okay. So it affects the scope that
The
we did on the network.
scoping matters.
Okay. So I need to extend basically
Yes.
to check the parallel roads if the
Correct.
excess traffic on this one.
So if you look at the sample network that I set, that is from the center, and then I make it bigger. So in that network at the sample
This one,
network.
sir, the
Yeah, at the bottom, yeah. Yeah, no, that you choose any of that here.
Okay.
There at the bottom, going down. There, ring. This is the core. Okay, a little bit slow. There. You can see the display network down. Oh, why?
The link made
The link did
the
not
links
show.
are not showing.
Oh, maybe scaling only. Okay. That's strange. So 50, maybe. The link is not showing.
Yes, sir. The links are not showing.
Try to select any.
Okay.
Not showing.
Yes.
Oh, that's strange.
Maybe the bandwidth already because it's
Or you refresh. You refresh this one.
okay.
Maybe still computing somewhere. Because you compute a while ago. Right. Okay. Now.
Yeah, now it's showing.
Yeah. Yes. Right.
Okay.
Bandwidth is using by that computation. Okay. So now you can go to ring 1, ring 2, and so on. Exactly the same. So I just expand, and then you can start to see. Sorry, exactly the same. Now I expand, right, the network.
Yes.
And then you can start to see whether this is actually improve the scoping matter or not. So up to N3, right? So then, okay, when you calculate the result, okay, will change. That means that there are certain part that change, there are certain part does not change. So scoping can be matter.
Hmm.
And then if you look at the microscopic also, this is interesting part.
Microscopic.
Yeah. So say macro
Any of the two.
and so macro comparing to micro. So this one is the one that you mentioned a while ago. How about if I want to do left turn, right turn, and then some turn expand?
Hmm.
So you this one is T, right? So go to the
Yes, sir.
macro level T.
Okay.
This is micro, right? So macro level T. So this is the actual thing that you throw a while ago, like this,
Yes.
right? Now
It's simple.
see, this one you assume that all direction is allowed, right? So
Yes.
now if you go back to the microscopic, microscopic T, now you can start to see this is the assumption about. Now you can band this one. For example, C1 to C4, all of these are C, right? But with microscopic networking, so you can just make it so that this one not allow or this is allow, and when you want to do what is that called, traffic signal, so because this is based on proportional, so you can also modify in this side.
Mhm.
This one is U-turn, right? And then this is turn to the
Yes.
right, and then this is the
So this one is through
yeah,
A1, C1, C6, and D1.
right. So you can also check the cross microscopic compared to the microscopic so that you can check.
So when I'm doing the intersection, sir, I check the inflow and outflow on the node. I model the intersection on the macroscopic as node.
Remember,
And
when
then-
you model with macroscopic, you assume full connectivity, right?
Yes.
Including U-turn, which probably not. So how meticulous you need to model?
Oh, but
now you understand.
yeah,
That's why modeler get paid a lot, because very detailed, yeah. Every intersection you need to model.
Yeah, actually, I'm very thankful for your tool, sir, because without expensive price, we can do this evaluation, rapid evaluation.
Right, but at the same time, modeler need to do detail. Okay.
Yes, and then no need for traffic surveys.
That you only need minimal. Cannot say no traffic survey. You need to have minimal, at least one.
To calibrate.
Yes, to calibrate. Okay.
And or validate the results.
To validate later, because you predicted, right? And then you get the maximum congestion, right? Then you need to check where in that year, probably in the same year or in the different year because you projected, in that year, whether that link have the same flow as you predicted or not. And then how much is the difference?
How about, sir, if I'm gonna project, say, 2030, year 2030?
No problem. You can project.
How I'm gonna go about it on the model, on this IFN?
the same model. Okay, the projection does not related to this one. Go to the slide on policy analysis in Moodle.
Trip gen.
No. In Moodle, in the policy analysis at the end. Yeah.
This one's a transport policy.
No. The second policy analysis. Yes. I think you can try this one. Okay. So go down. This is to find the optimum link. This one. Read this one. Yeah, the long-term prediction. So if you look at this, this is economic model that you model based on population, based on car, based on any that the same as trip gen.
Population growth, car
Right,
population.
right.
So I need the data to
You need to model,
have this
another
potential.
model, economic model, econometric model to forecast.
Okay, for example, sir, I have that one.
Mhm.
There is a suggested model for doing traffic growth rates.
Yeah,
For
So-
example, this formula.
okay, no problem. So you have already traffic growth rate, right?
So I just apply it to the base
Correct.
traffic.
So you apply it there based on, read that slide a while ago, how I apply. Okay, the maximum congestion and the flow is interchanged like this. Okay.
Yeah.
See here, starting from this year, okay, I got this. This is the maximum congestion, right? And then you apply certain policy, right? So in your case, you are only two. Okay. So then I can predict, no? Okay. So you can calculate by hand this one. Okay. How much is actually K? If you know the model, you can actually get how much, and then you can actually calculate when it will happen, isn't it? Do you understand? Say I get this, yeah, this is the base, yeah. So when it will, now how much is this? I cannot see the value. 0
0.61.
Okay, for 6 currently in year 2000, right? So
Yeah.
now I want to get maximum congestion 0.9. So then you ask, okay, how do you get the maximum congestion 0.9? Okay, so you put it into IFN, right? So setting the IFN with 0.9 of this one. So then you will get total flow, mu total flow, isn't it? The same network. I did not change the network, huh? Okay, can you see? This is the same network. This is your network, right? The stochastic.
Yes. The base network,
Yes.
the base scenario.
Oh, separate.
You
The
still
base
run.
scenario
Yes.
and the alternative you also projected.
Yeah. So another scenario for the prediction.
Yes, for the prediction is another one. But the same, because different network, right? So the same network now you predict, improve. For example, yeah, here you have 0.6 in that year, yeah, base year it is 2000. And then how to get the 0.9? Oh, to get the 0.9, so you input, okay, into the IFN. So, and then you will get the kappa, right? The total flow, right?
The total. Then use it on your alternative scenario.
No, use this into your model. Your model contain kappa,
Okay.
right? I know kappa, I know population, I know car population. So what I want to know is the T.
At which year?
At which year? Approximately. This is not exact, but if you want to go exact, so you can get the T. Can you see that?
Yes.
This one you get from IFN, okay? The
Yes.
T you get from the model, the economic model, the time, when it will happen. So in
However, my network is already congested. That's 2023.
So your network is already congested. So you can scope, bigger scope so that less congested. Maybe it will point in that.
Actually, sir, my superior is saying to load more traffic from other development projects. But I believe if you load more demand
More,
into the
yes,
network
more
that
work
is
on you
already
because you need to
congested.
put more detail.
Yes.
That's a lot of work. I understand.
Yeah. Also, sir, I just want to ask, would you say that is it right to say a force flow is the level of service F? You're already at force flow. You're beyond capacity.
LOS, right? You are talking about LOS, level of service.
LOSF, sir.
LOS is a function of congestion.
Congestion.
P per C, right? P per C is the flow per capacity, which is congestion. So
Yes,
I
sir.
did not use that.
At congestion rates of more than 100. So you're
Oh,
already
that one is F already. LOS
yes,
is
yes.
F already. LOSE is your capacity,
Yeah, 1.
right?
Yes, sir.
So between 0.9 to 1, that is level of service E. But your congestion is 160 something.
Yes, already F.
That is F.
Already F. What kind of intervention can can improve that
The
kind of
intervention should not be on the road if you are doing that.
should be on the demand side.
Yes, in the demand side. So for example, during the COVID, okay, so stagger work hour, probably using an internet-based solution of working. Okay, nowadays a lot of people are starting to work from home, for example. So we need to change our mindset rather than
Yeah, not really always working on the supply side.
yes. Okay, so at certain point, it's impossible to do all this. Okay? Because if you reach, for example, all the people already using public transport. Okay, so whatever infrastructure that you use is useless. But at this point, you can still improve. Probably you use public transport. Okay, so you can reduce the PCU value, right?
Yeah, we see you on for example, the buses
So
introduced
you increase the buses. So in that case, probably it will reduce the PCU value. Okay. So it is still possible. So you can simulate how many buses that you need so that from that demand.
The same way we did in the model
Yes.
split.
If you don't know the actual demand because you only have AADT, right?
Yes.
So you can put it back. What is the people movement? Okay. The current level you can get back, and then you can change after that. How many vehicles, how many bus that you need, so that you can actually cope, so that the PCU value changes.
And then propose a different
Scenario.
intervention.
Yes, intervention on the road network does not always the solution. Yeah, so probably public transport is the solution. Probably the best way is actually to use internet.
Sir, to use
internet-based work.
Okay.
Okay, internet-based activities.
To lessen the
remote
daytime traffic.
So look at it this way, if you want to understand. All the government work, okay, majority, not the public work, yeah, the majority of the government offices, are they actually information or materials? Exchange material or exchange information? If they are exchange material, for example, construction work, that is exchange material, right?
Correct. Yes, sir.
In that case, they need to be on site.
On site, because They
because
entail fieldwork
at this
work.
point you don't have the technology to change that yet. But if they are only exchange information, okay, including documents and so on, they don't need to be on site.
Site, correct. But the arguments are actually of, for example, they lease some office, they have that on rental, so they need people to go there to justify.
That is bad, right? Because you spend so much money on that, then you need to pay more
You
money.
don't need actually. And something that you don't need actually.
Right. So that is bad way of thinking, isn't it? In fact, you don't need to rent anymore. So in that case, you can get less tax to the people.
Correct. I'm
Right.
learning, sir.
Right. No, think about it. Is this material or information? If it is material, yes, you need to be there. If it is
Yes.
exchange of information, including this course, you see, we are using online. Why? Because at the same time, we are just exchanging information, right? Not really exchanging material.
You don't have to be present.
Yes.
And then actually you made sense of the activities even online.
Yes. So there are certain
Sir,
activities you cannot do it online, then do
Mm.
it on site, no problem.
yeah, in planning, sir, we have the field works, so we
Right.
cannot really do it online.
Okay. So, but there are things that you can do it online. Why don't we do it online? So
Yes.
the problem is probably in the management side.
Maybe,
They
sir,
don't try.
sir can also
Propose.
yeah, the full online mode. Aside from that, reduction in tuition.
Yeah.
Because we're not using the facilities.
Yes, exactly. Right. And then look at this. If we use online, what is the problem? The problem is actually the management, right? The employer did not trust the employee that they are actually doing the work.
That they are doing the work.
Right. So in
They
that,
even argue that work from home makes the employee stupid.
not really.
Yes.
Right? So
Yeah,
now
more
it
work-life
depends on
balance.
how you manage, right? So how you check the monitoring and so on, right? So in that case, not depends on the actual employees or not. It depends on how you create the system. Monitoring system, what I mean. So when you are at work, there's no privacy, of course, right? So must be monitored. So in that case, can create trust, isn't it? So can I share with you just one infographics?
Okay, sir. I'll stop sharing.
Yeah. So can you see this? These
Yes,
are
sir.
the input, the four input, no? The connectivity, the capacity, maximum speed, and distance, right? So based
Sir,
on
on the maximum speed, should we assume it as the design speed?
the maximum speed, the design speed, yes. But depending on your purpose of the policy, can you see?
Reduce. Yeah, if traffic
You
calming.
can also reduce, you can increase maximum speed by various things. Now, for example, you can reduce the side friction, the parking, the people selling on the streets. Okay. And the distance, this is especially I noticed in the Philippines, they always close the gate, right? In the residential area, they close the gates. So in that case, it will make the distance longer or shorter, even though they are actually very close to each other.
So on my kind of project, what is idea should be you increase the max speed and then you have shorter distances.
So you create alternative route. For example, use the residential area for the public, not just for residents.
For private use.
Or of course not the small ones.
However, sir, they are gated communities.
Exactly, that's the problem.
They don't want public traffic going in.
That's okay. In Indonesia, okay, so there are some rule. Okay, the law said all development, okay, must return back to the public after several years. So once the road network, even though it's built by the private, when they turn over it to public, then it's the job of the government to maintain. So that kind of law should be introduced if you want. Yeah, I understand this is much bigger than this project, but at the same time, if you want to.
Yeah, sir, I really appreciate the time and the inputs you.
So there are certain law that you can make to change, that not all road network should belong to private. Okay. Certain road network in the main trunk of the residential area should belong to public. In that case, government need to offer the maintenance of that road. With that, we'll create a system that is feedback system, meaning the government will not give permission to the residential area to be built unless the government have money to maintain. Can you see that point?
Yeah.
Right. Without that, government just give license whatever they want, just to get the tax, but never give back to the people. That is not good system. There is no feedback loop. Can you see that? If you want to create a system, you need to have a balance.
Yeah.
You see the karma system of IFN, Okay. So this is strongly connected. Come back to the original points. Okay. So the government cannot just take without giving. Okay. So in that case, when you give license to the private to build residential area, what will happen is up to certain years, okay, certain roads, the main part especially, will belong to public. That means the government will take over. That will increase the budget of the maintenance of that road. If the government is not ready, they will not give license. So with that system, you see, it's not just because you want it, but depends also the government is, especially the LGU, can we build maintain this road or not? You see, in that case, no more gate community, and then you will have more alternative route to use. So the traffic congestion suddenly reduce so much.
Yes.
The problem is because you don't have alternative route.
Yeah, the local traffic, especially on the at-grade, you cannot go anywhere but on the national road.
In that case, not enough. Whatever it is, not enough. Because you did not distribute the congestion to other place. So you need to redistribute the congestion. I have video on that, right? So you can check. We can actually redistribute the congestion so that balance all the people.
Okay, sir. I'll look it up also.
Okay.
Sir, the policy analysis, that's the lesson for
next week.
Policy analysis too, that's for next week, right?
Yeah.
I've gained an
in advance.
Okay.
Okay. So thank you. So
thank you, sir. Thank you, sir.
Yes.
I really appreciate the discussion we had today.
Right. So I hope this is useful. Thank you very
Yes, sir.
much.
Oh, because this one is a more complex problem than the one we did in our group work. Our group work is just what they call this. You have a development, and then we load it as a future scenario.
Okay.
The demand coming or the trips that can be generated from that development, you load it as a future scenario to the existing network. Then let's see what happens.
Yeah.
And then reduce or increase lanes. But this one is really a public investment.
Yes. So
The
big
proposed
money
project.
invested, right? So in that case, because this is your real project, so you go to the detail. Every
Okay.
nodes you need to intersection. Every intersection you need to check the detail left, right. Which one is turning ban? You cannot allow the U-turn, right?
Yes.
So you create that links.
And then maybe expand the network and see if it
Yes.
improve the congestion overall or the average congestion.
I have tools to convert to GIS into shapefile that you see in IFN transport.
So if I have, for example, the KML through
Yes.
the Google Earth.
Where did I put it? Is it in the model? Oh, there in the model. Can you go down in the at the bottom? There is GIS converter.
Where is it? In the Moodle.
Wait, I will check. I will share with you. So in the model, if you go here, IFN transport, right? In the model tab, at the bottom, there is GIS converter.
Okay, GIS converter.
Yeah, this one, if you have this node, then you can convert to JSON, QJSON, which you can use in QGIS or ArcGIS. Or you can
Shapefile for ArcGIS.
yes, if you want to convert to shapefile, for example, you can.
Okay.
So just convert and then you can upload from QGIS.
I can also do the reverse
Yes.
upload from, for example, sir, I have the Google Earth. I use Google Earth, and then it will return a KML file.
I don't have KML. This is only shapefile.
Shape. So I need to do it in
ArcGIS or QGIS, right?
Okay.
Okay. So and then you can.
Yeah. It the network modeling in terms of nodes and links would be the time consumed for doing that would be lessened.
Yeah, a little bit. But
instead of pinpointing each.
Big amount of time when I do modeling like this, big amount of time, usually we distributed the work into several people.
Yes.
For each intersection, you need to go to the detail, right? And then you make it very zoom it very big, and then you create a new node there that turn left, turn right, and so on. That part is very tedious.
Correct. Very tedious, but it's worth it.
Not difficult, okay? Just tedious and boring.
Yeah, sir, I realize it. It's just on my model, the simple model I showed earlier, it's just 50 nodes and 66 links. And yet I find it tedious already.
That much still macro, right? Not micro. Huh?
Mm.
If you do it micro, then
And then it's even more. It's even more.
right.
Okay, sir. If I have any questions, maybe I can.
Sure, please, anytime. Okay, even if the class is finished, you can just anytime.
Okay. Thank you, sir.
No problem.
Excited to present our work But sir, on our group project, we just compared the network performance as average, the average statistics. And then if it indeed improved, we just report on how it on those statistics. Or we need to test it if they are significant.
No need. So this
No
is
need.
group
Just show
project.
that congestion, delays are improving.
Yes, yes. No need significant level and so on. Otherwise, it's very complex.
Okay, the group is doing well.
Okay. So
What we did, sir, is reduce lanes and add lanes, and then combining those two.
reduce lane can improve.
It improves, but on our case, sir, it's the widening that is more. The congestion was reduced further with widening than reducing.
Okay. Good, no problem. So yeah. So see you next week.
See you next. Yes, sir.
Yes.
Sir, I didn't get the finals date, the schedule for the final exam.
The final
Is
date
it still on December 13th?
December 13. Let me check.
So we won't have
No
some
class.
makeup class.
No class.
No.
Oh, because you rejected. I offer already. So
This is for the optional for the optional lecture.
yes, for the optional lecture. That is for logistic mostly. Say we don't know. Not all of you become urban planner, right? Probably you will go to logistic company or transport company. Possible, right?
Yes, sir. And then we'll use it for traffic impact analysis.
Yes, exactly. So, but anyway, if that is only.
And then again, yeah. Actually, being a transport planning student, I realized you study for something you can get paid later.
The problem with planning is right now, yeah. So you cannot validate, right? After you plan,
no one
your
can
result is
check
true
your
or
work.
not. Nobody knows.
Even your peers.
Even your peer does not know. So that is bad. That is faith, no, not science, isn't it?
Yes, sir. Even urban planning.
Exactly.
The assumptions of the urban planners are not subject to scrutiny or validation.
That
It's
is
just
not science.
taken as it. Oh yeah, the results are
Not
taken
science.
as it is.
Okay. So that's what I'm telling. Look at this. I'm creating this IFN so that this become the science that you can actually check. It can be wrong, no problem. But once you get your model is wrong, so we can improve it, right? Oh, what's the problem? Why this not get the actual result at that year that you want? Okay. Oh, maybe you set some parameter assumption wrong, and so you can reevaluate. You can get the feedback. Without this, how can become science?
Yeah, they focus on saying that planning, being a multidisciplinary undertaking, is more of an art than the science. But yeah, it's really a
So I
science
will
because
tell that is not
balancing.
art, that is a faith.
Yeah, we're balancing land uses, and it should be based on quantities, not really on.
So I mean, need to be checked, right? To be validated on the field and that year that you plan, whether your estimate is correct or not.
Yes, and then recalibrate based on
And
that.
then recalibrate so that next time will be better. That's exactly what science is.
Yes, sir. That's the process they've been teaching, but it's not the practice. The process should be a feedback loop, and then it should be a cycle.
But how are you going to get feedback if you don't even know how to get that data?
Yeah.
Because you base it on average. Right?
Yes, sir.
Your result is based on average. Average delay, average speed.
Yeah, and then when you report it, it would be how much is reduction in travel time overall, how much is reduction in travel distance.
That is average travel time. You cannot get the actual real value. For example, okay, next year will be like this reduction. Is it true? How can you survey all of those people?
Yeah,
People.
it's lip service already,
Lip
just
service,
like
that is lie. That is not science. Okay. So that's why I said, no, this is not correct. The correct one is use the maximum congestion. Why? Or the maximum flow. Why?
Yeah.
Because using that numbers, you will know the location, right? And then if you know the location, you can survey there.
Hmm.
If you
And
know
then
the location
validate.
and you know the year, the month if you want, or the date if you want, okay, it's the date. And then if you know the actual time and you know the actual location, you can do the survey there, exactly there. And then you test whether your number correct or not with the reality. Okay. Most probably not, no problem. How much? The difference. Okay. If the difference is so much, oh, something is wrong with your model parameter, or something wrong with your assumption. Okay, or your computation, I don't know. Right. So if they are close, oh, within just 5%, deviation. Oh, our model is good, huh? Accurate enough. Okay. So next time we can do the same. Maybe from 5% you can improve it to 1%. So over time we can get better and better.
Yeah.
Huh? So without that validation, oh, based on average. Come on.
As we call it, sir, in practice, it's just table survey if that's the case. You just do everything in your table.
How to do the survey to get the average? Impossible. That means all people need to report to you, right? And then you do the average. That's not possible. Million of people.
Anyway, sir, I won't extend further questions for tonight. Thank you for your input.
No problem.
Maybe see you next week.
Okay, see you.
Yeah. Thank you.
Bye.
Thank you very much, sir.